Great pleasure. Thank you all for coming. First lecture by someone to give me all many questions. Thank you. Thanks to the organizers, Varun, Nordin, and Peter. So I've been trying to learn a bit about random since the past 1.5 years. I'll be able to tell you what I've learned. So let's start with some examples. So what are tensors? So you all know what matrix are. 2 by 2 or two-dimensional arrays of numbers. So tensors are multi-dimensional arrays of numbers. Let's see some examples. So very common way of representing images are as tensors. So first, you have to locate the pixel, right? So you need x and y coordinates, and you also need the value of the red field. So if I represent it as phi, then to represent the value of the, let's say, green channel at x position, right? So to typically represent those things as integral between 0 and 5. This is where you get 3 or order 3 tensors. Is my writing visible or? Yeah. Also, if you take videos, then tell me what should I add to this. Are I shining right? Right? So if you have black and white pictures, then you can represent that because you just have a single channel. You just related to images are you can have 3D versions of this. So these are popular in medical imaging. So here we represent pictures as two-dimensional, right? So there you also need an organ is a three-dimensional thing, so you need to locate three-dimensional, locate a certain location in 3 dimensions. So the generalization of pixels are called voxels, and anyway, let's say you measure something at a particular location at an organ, so that's the same. In more examples, if you have seen your background in statistics, then you must have seen contingency tables. So where these are basically arrays of numbers, right? Where you have a population, you group the population according to various categories, and at each cell you basically put the number of people in a certain configuration of groups. So I'll again write an example. So we have 3 categories. So the ijkth coordinate will represent the number of people in the population coming from the ith age group, the jth income group, and the kth region. In probability of statistics, you often deal with covariance matrices, right? we can of course look at moment tensors, which are generalization subsets. Basically, these are the arrays of numbers which let's say the other collect all the third order product. I will give one more example, which is my favorite, and this is how I'm interested in tensors. Of hypergraph. You all know what a graph is probably. You have a set of vertices and you have a set by pairwise relationship between the vertices. These are vertices, these are edges. Completely write this with them. The vertices are 1 to n, and the edges are certain subsets of the pairs. So these are good for okay. So what are adjacency matrices? Adjacency matrices associated to a graph. The matrix which encodes the adjacency or edge relationship. So you put an edge, you put an 1, the ith location if there is an edge between I and x. Then there is 0. Right. No, so these are some examples. I'll give you a formal math definition after we see some examples. So for the time being, just think of them as multidimensional arrays of numbers. And these are some examples where we see such multidimensional arrays of numbers. So hypergraphs capture multi-way relationships. So these are like pairwise relationships between vertices. So again, you have a set of vertices, and edges are basically subsets of one. You allow any number of vertices here. E is just a subset of the powers.
You write the question. Multiple rules have like one element subsets and only
You can have one element subsets. I allow it to be efficient, but yeah.
and also in the empty
This is the empty is also possible. You can have. Okay, so examples are multi-way relationships, for instance, maybe I, Krishanu, and Shiva are friends. So a triangle or a a three subset denotes that relationship. And of course, you can encode that information in a tensor now, right? In the same way. So A, I, J, K will tell if I, J, K, then my H. It's
subsets of same size.
not necessarily. So if you look at subsets of the same size, that's called a uniform method. But in general, you can allow subsets of different sizes.
Things that can have different models.
Yeah. That's a good point. So if I want to represent three-way relationship, I will have a third order tensor. And if I have various types of relationship of different order, then I have to take all those tensors. Okay. So very good. So these are some examples. There are also examples coming from physics, like stress tensor, elasticity tensor, etc. But I'm not very familiar with those, so I'll just stick. So yeah, so what are tensors? Let's now formally define things. So yes, it's a multidimensional array of numbers. That's one way of looking at it. So mathematically, just like a matrix, the linear map between vector spaces can give the definition. So a tensor can be thought of as a multilinear map. So if you give me a linear multidimensional array of numbers, I can of course define a multilinear number. And conversely, if you give me such a multilinear map, I can look at what it does to the basis vectors, and then they will give me that multidimensional. I'll try to use the script T for script symbols for tensors. By use of notation, I'll be denoting the map by that. This is one view. You can also think of a tensor as a member of this tensor product of different vectors. So in this view, of course, you can write this. All of these are equivalent vector things. You can write script as a linear combination of elementary tensors. Just like matrices, you can write as linear combination of elementary matrices. Right? Similarly, you can represent it as linear combination of these elementary. So for most of the mini course, I will focus on the case where the vector spaces involved are all Euclidean spaces, real Euclidean spaces. You can of course have other general vector spaces as well. In some cases, I will take complex index C to the n. But for most of the part, I will stick to real vectors. Real Euclidean. Okay. No, so those are just arrays of number, and that particular representation is important. Like for instance, in hypergraph, I specifically want to represent it as 1 if there is a is between people and 0 otherwise. That 1 is important, right? So I write it in that way is important. As you are probably alluding to, certain functionals of the tensor are sort of intrinsic properties, and they will not depend on the choice of the basis. But in many of our examples, actually, the one proper basis will speak, and then we'll just represent with respect to that basis, and most of the time that will be this standard. Okay. Let me also define continuous net product. Given two tensors of the same order and same dimensions, define continuous product. Do you know what the definition of product for matrices are? It's the same thing. These are these are real tensors. We have this. If I allowed complex, then fine. Yeah, this is the outer product of two vectors. That's the so you think of the matrix case where E1 outer E2 like this. So it's a vector space, and these are the basis elements of the vector space. In general, if you give me arbitrary vector spaces, you want to VK and some bases there, right? Here I can construct their tensor product and the basis vectors there. Symbolically, these are. What's different? Yeah, these are the different ways of looking at the thing. So first we looked at things as multidimensional ways of arrays of numbers. If you give me a multidimensional array of numbers, I can define a multilinear map like this, right? And then you can evaluate that map as the vectors. I get back those coefficients. The other hand, you can also define things like this. It's a member of this tensor product of vectors. And then how do you recover the coefficients? These are basically the coefficients, the basis expansion with respect to the standard basis of this. Sorry, yeah. Yeah, J1 to J. So all possible. Is from the
I1 by R, I1 by R. Like how does that work? Between those two terms.
these two times?
Yeah, those
That's real number.
just real number. Okay.
So when I define that, I'm only focusing on complex or yeah. It's a complex, it's a complex here, otherwise it's yeah. Okay. And then of course associated to this is the Frobenius norm. See that this is in fact okay. So this linear map I can also express it in various ways. See that this can also be written as the Frobenius linear product between the tensor T and my G and tau are the leg of the umbrella will keep changing. So, and tensor like this. These are called rank one tensors. So again, I will define. Define it in terms of that representation. So I will make like that. Okay. You know what? Outer product of two vectors is right. X y transpose. How does it look? X I x y j, right? That's the I and element. So and
One tensor x to be different.
yeah, of course, it's different. So, like this can be different.
Right.
Yeah, I get it. Right, so these are the you can think of this. Ith element is given by the product of x and x. Yeah. So this is the coefficient in front of this system. The sum. These are rank one tensors, right? And I can it depends on where you the definition, right? How you so it's conjugate linear and in what coordinate it depends on that. Anyway, I'll work with real tensors.
All of this example.
Yes.
And the one
Right. I mean, coming to that problem, it depends on the problem. So, I think the physics examples they do have some meanings. So I'll give you one.
okay.
Yeah. For the also they use that as a convention. Yeah. So for instance, this norm. I want to point out one thing. This is like an intrinsic quantity, right? In the sense that if you rotate the basis vectors orthogonal map, that will not change the. So yeah, certain aspects of those maps have intrinsic meanings, but the representation might depend on the problem. Okay. Yeah, and I'll just give one more notation before I. So if you have a matrix, you can multiply that from the left and from the right by two matrices. So tensors also have a similar thing. Each mode or each dimension you can transform according to a linear transformation. So this. So that here. is a vector.
And on the right hand side, you have x9, 1, x9.
So that's again a very good point. And yeah, I'll be drowning in the sea of indices very soon. So thank you.
I1 goes from 1 to n. Right.
I guess I messed it up there as well. No, but this is correct. This I think I corrected myself. I think I know what it is. Yes.
Okay. 1, 3, 1 xk.
Yeah. The index runs from 1 to n. Which is interdimensional.
And k would run from 1 to r.
K would run from 1 to r. Right? So this r is for the order of the tensor. Yeah. Okay. Also, like these different dimensions, they are typically called modes or legs. So I'll often refer to them as modes or legs. Yeah, so just coming back to this, suppose you have a R order tensor like this. Just like a matrix can be multiplied on the left as the right by the matrix, you can multiply now quantity by a bunch of R matrices. Okay, I will copy that instead in the index. This is defined as R take R. Sum over this I. That would give me another multidimensional array of numbers.
So the element
Of that array, right? So now at the linear transform or multilinear functional level, what is happening? What multilinear functional does that array of numbers correspond to? Right? So this is the new one, the RS elements of that. Let's think about the what does it mean by multiplying from the right by matrix?
by the matrix. Like vectors in the tensor product, basically, there was column vectors, right?
Yeah, column vector. I'll definitely try not to distinguish because if this is outer product and this is dot product, that becomes confusing. So I'll try not to distinguish between column vector. Okay, So what do you think? So yeah, typically what it means at the level of this transform within the matrix at each mode I'm applying a linear transformation, and that's the thing.
We can think of it as like applying the matrix like the bullet, right? Like the first matrix to the first vector and second vector.
Exactly. But this is the corresponding linear, linear. So this is the graph. So you write down R. We need to define the map. Then we call it. We can also, basically we'll denote by vector notation the map and the array by the same thing. That is by map. You did that game. Now, can you quickly tell me then this will also be written in that way, right? No, the notation I will use. Yeah, so this particular multivariate map, so you start by this, I will also use this notation. So people have come up with lots of different notations. So yes.
But am I square matrix?
Now, MIs are you have to match the dimension. So let's say I want to get tensors of the form right. Then you have to make sure that the dimensions match, right? So MI is what? Some order. Right. Then I cross in, right? So here is another notation I will use. Just uh, and so the fact that I mentioned earlier that Frobenius norm is rotation invariant, that you can succinctly represent by this, right? If you take orthogonal matrices, Frobenius norm of this, then as the Frobenius norm of the within the right? These are orthogonal. Column orthogonal matrices, you take all different dimensions. Yeah. R matrices. So just like you have a matrix A, you can multiply this by matrices, one from the left, one from the right. It's a generalization of that. A is my matrix, I'm multiplying it by matrix. I mean, you look at the J1, J2 element of this. Exactly have yeah, right.
So also have to be less than or equal to the numbers, right?
Yeah, yeah. Of course, you have to have a basis.
Right. Yeah.
All right. The plan next to is next is to define the notions of eigenvalues of tensors. Okay, so what do I want to do with tensors? So I want to develop the analog of random matrix theory in the context of random tensors. You have tensors, the elements will be random variables. Right? And so you know in random matrix theory, you have a random matrix, then associated to that are is eigenvalues. So you can look at the empirical distribution of the eigenvalues, right? The largest eigenvalue, etc. Study the behavior of those random objects as the dimension goes to infinity in such. Right? I want to come up with a similar theory for tensors. As you see, much time I have. 10 minutes. So, as you see, the concept of eigenvalues is a bit murky in the context of tensor. And many things that are useful for random matrices are completely baked down. So, we have to see what we can. Any questions after this? So this is just a very basic intro to what tensors are.
I'm guessing orthogonal with no unitary if you work with like C.
In C, yes. No, this is not a matrix. So this is a notation for this linear. That I will use again. So I just wrote it there. So the yeah. So here you have a bracket as well. These two are distinct concepts. So this particular notation is convenient for writing eigenvalue equations by this is doing the same thing as this multilinear function. It's another notation. There are various notions of eigenvalues. I will define one type of eigenvalue that is to be thing. They are called E eigenvalues. And also E eigenvalue is the underlying vector spaces are C to the n, and B eigenvalues, Z eigenvalues, we are working with here. These are basically I think I will need another notation. The solution of this by this, I mean the outer product of J copies of XVII itself. So this on the eigenvalue. So what is this? I don't think I have defined this. So this is basically you sum along every other leg, but there are r minus 1 dimensions here. Okay. This is the order R tensors. Okay. You sum along every other leg but one. At the end, what do you get? You sum along R dimensions. You get a weight. That okay? Yeah. So I'll just define. So here this means precisely this. I have r minus 1 copies of x. Okay. I'm taking the outer product of r minus 1 copies. The typical entry is like xi2 to xi. I'm taking that product, summing up the order challenge. We're keeping only I1 free. So yes. It's not linear. That's one of the first problems. Yeah, then it's location dependent. Why you
Right.
it matters. Sorry.
You can only give the first sig free.
Yeah, so this as it turns out, so as per this definition, I'm fixing this I1, but soon I will basically switch to symmetric tensors where it doesn't matter why. This definition depends on that. Right, so this is a vector, and this is the generalization of the eigenequation for like matrix.
RD. X in RD.
Yeah, okay. So eigenvalues, when I talk about, I will assume that all of the dimensions are the same. Just like for matrices, you talk about eigenvalues of square matrix. Okay, so
Like n equals n1.
in R, they are all equal to it.
The left, that was the I1 and N3 right?
Yes. This is the I1th entry of this vector. Yes. So you have a n-dimensional vector. What sort of thing is does this solution? Yes.
R minus 1 outer product. R minus 1 meaning outer product.
R minus 1 many outer product. There are J is the order J tensor whose entries are xi1 up to x with respect to the standard basis.
Generalizing the product of multiplication by matrices.
Other tensors as well. You can make a more general definition. I don't want, but it will mess with indices. So this is the only thing I need. So
It's which is the convention that you're fixing I1.
yeah.
Then you put just the last.
Yeah, then you get a different thing.
Yeah.
Different. So for symmetric ones, you see. Right. X. So you say that a solution of this equation x lambda is an eigenpair. Lambda is an eigenvalue with eigenvector x. So this is an equation. This defines an equation, right? System of equations in x and lambda. They're scalars, yes. No. This is the I. Okay, so the I1th element of this vector is this lambda x. This is a vector. This is a vector. Oh, okay. That may be the source of the. See, what I'm doing is I have r dimensions. I'm coming along r minus 1, right? So one dimension is free. You vary that, you get a vector. Right? So this is a vector whose I1th coordinate is this now. Equals lambda x. Yeah, x to be non-zero. I've already written it here. So let me just define it. So solution.
What the next line ones that side we don't think like all of them need to be equal. Just at least for it.
Let me say that lambda x, then I. As you have to point out, here I1 is fixed, so I'm only summing over the rest of the points. So it's related to that. Yeah. If it happens that x has real entries for z under zi, x is a dimension entries. No, these are the coordinates. They vary between, these are indices, they vary between 1 to n. Right. So I'm writing x as x I j, where j runs for xj, where j runs from 1 to n. And these are various indices we vary in that state. So if x is real vector, then we call lambda x as z eigen. Do eigen tests. In general, it is in CN, but if solution so lambda you can allow it to be in C. Of course, if I assume that R is in R and lambda has to be now. These are okay.
Lambda is also
Has to be real because the A is real, X is real, so yeah, maybe 5 minutes. So think about the question whether such a thing can exist. Like we have to show that an architecture exists.
That one where you keep one of them free. So basically, why are we doing this with like one is free? Why don't we just do like X test or R? Why R minus one? Like, why do you want to keep one? Oh, then you want to get it. Then you do it like 1 point, 1 point.
Yeah, it's a theorem. X is non-zero, yes. X is non-zero and
Yeah, I have another question. What are the hypergraphic we So like like what the interpretation would be if like the hyperx that had like one element of that or like a really like real like maybe one element of the like a self.
so you mean the empty subset as a hyperx?
Yeah, so basically the set phi is in the because you said subset 0 to the
Right.
set, right? So phi counts as subset.
Yeah, I guess.
It's really
It's like saying that how it is.
Right. Yeah, this is a good method. Like we can just include our X to the
Here, I will see that non-linearity is doesn't equal. What scale is it? It's a convention, so sometimes
one element. Like is it like a self loop or is it different?
no, because the point is not connected to it.
With the one order interaction, whatever that means.
What can you say?
Right.
Exactly, yeah. You can make two big matrices. Yeah, I mean, this is clear in the sense that you are seeing how you are dimension. What has some meaning? But if you put attention in a vector, you can do it in any way, number. You're meaning something.
Okay, so you want to keep that in. Because when it is think of this way, it's not the same as that figure vector. There's a probably this is the isomorphic.
In fact, these are map between the space of matrices and functions, right? Here also.
Only thing that but think of it as isomorphic map. Yeah.
No, X is a vector. Vector. Outer product is between two tangents, the one. Yeah, you get a one tangent. You can ask him the it's a good shot, yeah. You have to match the yeah, so we have to match this NI so that this is defined. We have to match that. So I use that. direction. Yeah, I mean, it depends on component. Component wise doesn't matter. It depends on whether you are thinking of it short case or
As your audience will be sponsored. The camera is using. Oh, really? Yeah. Very first class, okay, you have the streamlines in the class, you can think of vector space of that. So something like that. Right. We can define a prediction, things like that. Well, coming from just from the school, that was quite a shocking way to write the visual. Just basically, so that's it. And you said
or ordered.
R. But this X has such a number of elements as well.
Yeah.
And so we are not here.
Okay, those are there. So RN1, RN2.
Right. So what we are going to take all the analyze shapes.
Most of the time.
And also symmetric.
Also symmetric because otherwise.
I mean, you have to keep track of this.
There's a proof will be symmetric. I can put this things like this.
I will keep talking.
Because you have multiple variables, like nothing that. Yeah, just check that.
Even one option when you have students. That's one thing I will make institutional structure and you're still using the same thing. So I take the base Corresponding and instead of anything is right. Let's start at so one of the right and I always get confidence in right column and
Two. This is the vector. So AX equal to lambda x in the
So here it's
I1, I2, and xi, nothing else. I probably mentioned it. I don't think so. So D here, Abdul just asked me here, E refers to deeply there. What does D refer? D refers to the person who invented this. Now, he didn't give the name, of course. Another person called it here. Okay, so do such things exist? Is the question. So the general existence result is difficult to prove. It uses Bezo's theorem from algebraic geometry. Not going there. So assume things are symmetric. Then we can very easily prove the existence. So what are symmetric tensors? So it is called symmetry. You can also define it in terms of the multiplication, you multiply by permutations. But I'll just write it like this. For all terms. Okay,
E I sigma 1 through I sigma
I
r
see.
one
I see what you mean.
Yeah.
Yeah.
E I sigma. E I sigma.
You're right. Okay, so I will assume that all my tensors are symmetric. Then the question is, does a eigenvalue exist? How do you prove that eigenvalue exists for a symmetric matrix without using fundamental theorem or algebra? Use the relational characterization. So what we'll do is we'll look at this multilinear map and basically put x in each of the coordinates that gives you a homogeneous polynomial. Take the linear map with x in every coordinate, the homogeneous polynomials are variables. So to see whether this is a function, real valuing function, right? We try to maximize it over the index. Of course, the maximum minima exists, right? But if you use let's say Lagrange multipliers, let's see what we get. Want to optimize this? What is the gradient of this map? Well, that you can check. I don't know what the gradient is. Precisely R is dot x minus. So critical point will satisfy this. That's precisely my eigenvalue. The Lagrange multiplier. Get this. I mean, yeah. Symmetry is. You see, you can always associate a symmetric form to any non-symmetric R form, right? So it doesn't correspond. Of this. They are precisely the eigenvectors and eigenvalues. And differentiate how we get this R is coming from because otherwise you have a sum. If it's a multilinear function, so it goes from R cross R in R times, right? No, sorry. I have already put the same vector everywhere. This is just R into no. This R, if you differentiate, you get R minus 1, which is the vector. One leg I haven't found over. If it's the number, so acceleration makes sense.
Momentu, R equal to 2, this is x transpose x.
Exactly. This is a quadratic form, X transpose X. It has the compact set, so you have saying that any solution will satisfy this, and then critical points and critical values of this are
And that solution gives you the
eigenvalue here. That's a very good point. So, how many eigenvalues do we have for matrices? N, right? Most. How many for tensors? The next. While you think about it, I will point out a feature of the non-linearity that you added earlier. So this gives you the existence of Z eigenvalues or not real symmetric tensors. The answer is yes for general non-symmetric tensor as well, but that's outside the scope of.
that's a different element. Oh, yeah. So that object. You say that the composite
This is sorry. What shall I call it? Let me call it L. Yeah, so L is the objective function and critical values and critical points to solve this equation and so. Okay. So for matrices, if you have a eigenvalue eigenvector here, right? Then if you multiply by a scalar, that will also be an eigenvalue eigenvector. Here you see along the case. So if I multiply by the eigenvector, the Z eigenvector by alpha, right? So I get what? I get alpha to be r minus 1. And I'm assuming that this is an eigenvector, Z eigenvector. So this is alpha to the r minus 1 times lambda x, right? But I want to get alpha x, right? R minus 2 times lambda times alpha. Yes. So if you multiply by alpha, then you get lots of different eigenvalues, right?
Yes.
Unless so we'll of course consider them as equivalent. So this defines an equivalence. Two eigenpairs are equivalent if there is a alpha such that the eigenvalue and eigenvectors are related like this. Two eigenpairs are called equivalent if there is so the lambda prime is alpha r minus times 1 and beta prime is Sorry? Non-zero alpha. Where is the yes, non-zero. Yeah, so what do you think? How many eigenvalues can a tensor have? Modulo that equivalence modding outcomes. Can you get this? So again, matrices are n unity, right? If it's private piece of order.
You get this R.
Okay.
R to the end.
Symmetric, so if you formulate the increase of the solution,
Okay.
gives you n factorial when you kick the lambdas, same one, change the b.
I did not understand the argument, but your answer is correct.
You just formulate the coordinates of b.
Okay.
Since you're getting the left hand side will remain unchanged. The left side of the defining equation will remain unchanged.
So you are computing the coordinates of x, right?
Yeah. So the left hand side of the defining equation for eigenvalue will remain unchanged. Because A is symmetric.
A is symmetric, yeah. That's true. Yes. So see that already gives you 9 factorial. Yeah, so
Each lambda you get
each lambda you get.
multiple of n factorial maybe because I don't know how many real size derivatives.
Okay. Yes. That's actually good. Yeah. So the answer is yes. The answer is exponential for r greater than or equal to 3. In general.
Exponential
In R or in N. So if this was correct, it is about R actually. If I write down the exact number,
the solution I was giving was only giving n factorial.
yeah, but you are not giving. You're just taking one eigenvalue and then changing the eigenvector. Eigenvalues can.
So I mean,
Yeah. So there is an exact formula. So let me write it down. So there is an exact formula when you let it be an E eigenvalue. That is, you allow complex eigenvalues. So number of E eigenpairs is R minus 1 will be any minus 1 for R minus. This is for R greater than or equal to 3. For matrices, we know it's just n. If you want to restrict to z eigenvalues that you want real solutions, then there is no clean expression like that. But probabilistically, you can say how many of the eigenvalues will be given to make the entries random. You'll see what fraction of these are given. Because of the non-linearity, so I'll show you one example that will tell you immediately how the non-linearity. Here's a question. Okay.
You're on. Yeah, LPS is on your top. That's the top. And then you can see is that, yeah.
Okay, so let's look at the simplest thing, the diagonal. Okay, so let's just take a diagonal then and try to see if you can find some Z items. Okay, so this is my equation. And for a diagonal tensor, tell me what would it reduce to? What is the left hand side? The ith element of the left hand side, for instance. Yeah, so unless all of them are equal, you get 1. So it should be xi minus 1. No, the ith element I'm going. These are vectors. We have the ith element. So here, unless you fix that I, all of the things are 0. The I element that's 1, so let's get xi here. So you get these equations. The r minus 2 is exactly r minus 2 is that one. You have to solve this system.
XI is not same. XI is not same.
Yeah, xi is done.
Solve the XI is
Yeah, maybe you will use the piece. Yeah, assuming xi is done. That's a good point. So that gives you some degrees of freedom, right? I can make some of the xi is 0, and on the others I will solve the equation. Yeah, let me call S to be the set of non-zero elements. Yes, let's call the size K. And then I have a extra relationship where I want things to be orthonormal, right? So this is one. This is one more thing that I have. So what I will do is I will make things I'll make one more simplification. Let's assume that all of them have the same value. All of these xi have the same value. So the vectors look like gamma, 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 and their series. Then what you get? This gives you constraints. Gamma times your xi is equal to gamma for I in S and 0 other. Let's look at vectors of this form. Then you get gamma squared times k is 1. So gamma is. And then what about lambda? Now assume that xi is 0 at that coordinate. Gamma to the till minus 3. R minus. R minus. So for each subset, you have how many? For each subset is, this is the eigenvalue. And how many eigenvectors can you pick? I can just flip the signs, right? So 2 power k.
I guess for every unity.
Yeah, for complex you can take other roots of unit. Let's just focus on the real persons here. And the eigenvector should be just there are 2 power k many. Keep the signs. There the coordinates. And k, these subsets you can vary, right? So it's a sum of power k into h. That already gives you something exponential. All right. And these are z eigenvalues. You have a complex system. Okay. So now I will point out another strange fact, which is not true for matrices but true for strange facts. For matrices, all the eigenvalues are of a symmetric matrix are real. But for tensor that doesn't. Because was continuous, I can take other elements of any complex eigen.
Choices.
Of the subset, right?
Science.
Yes.
Then a mapping of this to matrix case. Or is it the critical case?
I don't know if there is a mapping to the. So I don't know whether you will always have exponential number of real eigenvalues. Not just on average you will always have, and this is one instance when you have. So I don't know whether there is an explicit mapping. Yes.
These are all eigenvectors that we enumerate.
Yeah.
What about the eigenvalues? How many eigenvalues?
So you can take any gamma. I'm fixing a gamma, and so gammas are this. So I'm giving you a particular choice which shows that there are exponentially many equivalent eigenvector pairs. That's a very complex equation. There are lots of solutions, lots of other solutions. This is just a class of solutions. Exponentially.
Do you have any concept of characteristic polynomial?
Yes, there is a concept of a characteristic polynomial for a different notion of eigenvalues which I have not introduced here. Unfortunately, dealing with determinants is quite a mess, as you can imagine. So I'm not going to. Not-
What does an eigenvector represent?
There is no immediate representation like the case of matrices, the meaning, right? You have some directions around which you. There is no such. Sorry? There will be. There will be use for it. Let's see. Reconstruct the tensor. So there is no spectral decomposition for tensor. I mean, there are certain decompositions, but they are not as deep as the spectral decomposition that we see. So again, you might ask, so from matrices we have the concept of a rank, right? Yes, again, there are multiple concepts of rank and they are not bigger. So the one, since I mentioned it, I will write down one definition that will be useful for us. So define the rank of a tensor. Smallest R, or smallest K, so that A can be written as a sum of rank K tensor, rank 1 tensor. Each of these are rank 1 tensor. What are rank 1 tensor? I have already defined the rank 1 tensor. This is the outer product of R. These are rank 1. So I think this is quite difficult computationally. In fact, it's going to be pretty hard for R bigger than equal to C. Findings with composition like this, if you know that it is not right. One problem here is that you know this fact that if you give me two eigenvalues for matrices which are different, then their eigenvectors will be orthogonal, right? Does that have to be the case for tensors? As you can see from the defining equation, it did not be the case. So a clean partition of eigenspaces and spectral decomposition does look good. So now I'll now move to random tensors and introduce randomness. Before that, I need just one more concept that are singular values. In fact, I don't need singular values. I just need the concept of operator norm. But anyway, so when tensor A, we define the operator norm as max the two objects here, where these x's are all unit vectors. Right? This is how we define the operator norm. You note that singular values have a similar interpretation, right? So with this exercise, you know the usual definition of singular values. You show that the singular values are vectors are the critical points critical values of this multilinear function. Okay, so what is the manifold? So let me try it in this. That is on the solution top at the critical point. And directly define the Lagrangian is x transpose y. This is another way of defining singular values. As the usual singular values are singular vectors are the solutions of this. So that's an exercise.
Sir,
Oh, yes,
sir, hello, sir.
yes.
I am so now since we are talking about the critical, the singular values and the singular vectors of a say of a, we know about matrix. How do we go for tensors here? Since we have the notion of the eigenpair, do we go for
So we will define by equations like this. You have the multilinear map, you put a constant and singular values will be the solutions, the critical points of that objective function.
for matrices? However, there is a interpretation the in
Yes, right.
for matrices, singular values have the interpretation that they are the
Right.
positive square root of the eigenvalues of say of A transpose A.
There is no such interpretation here.
What is the interpretation in this regard?
This is the solution of this equation. That's the interpretation that I can give. You know,
Okay.
the interpretation of singular vectors as the, for instance, the eigenvectors of A transpose A or A transpose. There is no such relationship.
Okay. Okay.
But you can make sense of the operator now.
Hmm.
And it is the largest solution of that equation in the matrix. So I'll come to the eigenvalues again, but in the interest of the time, the simplest thing to start with is the operator. So I will take a random tensor, ask the question, how large is the operator, not of a random. Okay. For a random tensor. Yeah, so I have introduced one constraint on this. So with this, you can also do that, but with this, you will get the exactly this would be the singular value, it will be a less singular vector and right. Okay, so let's ask this question for random matrices. So there is a random matrix whose entries are let's say Gaussian random. Right? So how large is the operator norm of such a bit. What is the order of magnitude? So it's an n by n matrix. Each entry is Gaussian, they're all independent. Square root of it, right? A random matrix is in fact, in this case, you actually know the precise asymptotic. If things are Gaussian, which means you have variance 1, then you actually know that converted to Q of So here entries of A are IIT standard Gauss. So I want to do the same thing for general tensor. The entries are IIT random variables. How large is the operator? So in general, yes, it is again. Okay, so let me just write it down. Let we random tensors with so let me just living in one R then the operator norm in the order to which log R or log no, log R is converted. Okay, so we'll prove that operator norm is this with high probability.
This is a random tensor.
Tensor whose entries are random variable, IID random variable. So think of this as a multidimensional array. All the array elements are IID random variables. Just like a random matrix, the entries are IID random variables. They are not assuming any symmetry. Okay? Entries are all IID random. For this, in fact, I don't need them to be identically distributed. They can be just independent. So what assumption do I? So yeah, so let me just. This is written for normal, but let me just write more. So this is valid when you make the entry sub-Gaussian, so the tails decay as fast as here. AI on part independent sub-Gaussian. So what are sub-Gaussian sigma square random variables? Well, I'll define it in the moment generating function. Also, okay. So independent zero mean sub-Gaussian sigma square. So a zero mean random variable is called sub-Gaussian with variance proxy sigma square. If the NGF satisfies this So basically the tails decay faster than, or at least as fast as a Gaussian. How much time do I have? I do. So then it's probably not.
Could I ask, you just have a big O here, not a, say
Yeah, big O with high probability, so I'll make it precise.
yeah, but I mean, so you have this log R.
Log R, yes.
Yeah, but that might not be sharp.
May not be sharp. I'll just, yeah. In fact, we have a limit result as well, so it's definitely not sharp.
We need to calculate sigma square dependence at this time.
So this was written for, so yeah, you just see scale invariant, so yes, put the sigma. So we will prove it in the next lecture, but let me write down some properties of sub-Gaussian random variables. Yes.
What's the mean which n1 to n or going to infinity can only.
This is a non-asymptotic result, so I'll tell you what the probability is. So the probability will be going to 1 if you send n1 and k in a certain way to, but you can do it in a multitude of different ways. I'll give you exactly probability of one. Yeah, so let me just write down some properties of sub-Gaussian random variables that we'll use for its proof. And I'll put this as an exercise in an exercise sheet. Suppose, so for simplicity, I'll write x follows sg sigma square. Suppose x is sub-Gaussian with parameter sigma square, variance from sigma square, then you should get still guess. Of course, a Gaussian is a sub-Gaussian. Another important example is our bounded random variables. So the first one, the simplest bounded one is Bernoulli or Rademacher. So suppose x is Rademacher, x is plus minus 1 with probability half. Okay. So then show that x is sub-Gaussian with parameters. Guess. With 1. So try to get a bound on the moment generating part. And here's a result. Use 2. You can do it in other ways, but use 2 to show that any random variable, any x, which is bounded between a and b, any random variable x, mostly bounded between a and b, is sub-Gaussian with parameter b minus s square. You can improve it a little, but I want you to just use 2 to prove it. And the final property that we will need is it should give me a bunch of Gaussian random variables. Okay. So suppose let's take it through. So x1, x2. x1 is Gaussian sigma 1 squared. xr is Gaussian sigma I squared are equal to 1 and 2. And they're independent. Then A1 x1 was A2 x2. This is also Gaussian parameter. And just like something. Finally, suppose x1 xn are Gaussian sigma square. They are not necessarily independent. They are Gaussian sigma square. All of them are Gaussian sigma square. Then you can this bound on their maximum. So this is at most 2 sigma square log. These are all the ingredients that you will need to do that result.
These are the IIDs.
They need not be independent. They are all Gaussian with a common parameter. They will show up here.
Now is bigger than or equal to 3. Matching load. Which one is there?
Yeah, there is a limit result. You can characterize what the
What is forward? There is overbound of the same order.
yeah, so in fact, I want you to think about it. If you throw a log term, it will be able to show a log bound of order square root n. So that's an exercise, and I'll discuss it maybe tomorrow. Show that with hyperbola. So I am deliberately keeping it here so that you can do whatever you want. So that yeah, so let's stop here. An announcement on the WhatsApp. Yeah. Yeah, so I was now depending on the tracking, I is constant. I can be practical. All but there I don't care. It might. Yeah. This is not a simple result for our but then the results of
These extras here are just standard like real value values.
What did you do?
Okay, man. Yes. That's the you want the character.
Something that would be a little very like just done it in the usual way. Yeah. Still, I mean, it's a if you view it on the tensor space, it's just linear, right? Like
Yeah,
the
on the
base is-
tensor space,
yeah. And then the dimension of the tensor space is like
N1 times.
N2 times. It seems like if you take the matrix. Yes, it is.
Yeah.
The operator. It's
Yeah,
they should have the products here on the top.
Yeah,
So there's something I'm missing. I mean,
they're
clearly.
different. I mean, they are
So
not
it's
the
just
same.
the operator nome's different here.
The operator now, if you view it as a metric also. In fact,
Because it's your all the xi's are it's not on the sphere in the tensor space. You're not taking you're taking the super
in fact, that's a trick that you use several times. You need a matrix of so for matrices we have extension theory, right? And
yeah. I see. So you're taking a super over us.
How are you?
It's like right, you
It's like your.
oh, I see.
I think that's the first the Cartesian product of several speeds.
Right, exactly. Yeah, exactly. So you're taking it over.
Okay, different.
Okay. So then is it not, I mean, it's not really, it's somehow not helpful to think about this thing as an operator, a linear operator on the tensor space.
Not really.
Yeah, just sort of
Because then, yeah.
whatever you want to use it for, that doesn't give you information.
And people.
You and IT formula.
Yeah. Yeah.
There are various different kinds of movies and you get different
Mainly these days work on rough patterns or?
No, not at all. I mean,
have hard dimensions, right? Even
nowadays
good
working
dimensions. You can say that my rows will correspond to one side and the rest will.
Sure, right,
So
yeah.
that's a.
Usually random geometric objects.
Oh, I see. Yeah. I see. So here you're right. You're treating each xi
Like
as its own thing, but then you could actually group
I
them
just
together as one.
for the
Those guys,
only I have diverged.
and that's useful in some settings to kind of do
I
that.
mean,
or-
these are.
I'm still interested in that.
Those are elite boundaries. They give you upper bound.
I see. Okay.
These are
Convince the student that both of us know that this rough path stuff is really cool and these kind of.
Yes, I mean, it has a lot of application. Sure, I mean, it is still, it's just that I have stopped working.
Got it.
Yeah, particularly
I see.
And then the round state corresponds to this.
Martin errors,
Okay.
regularity structures.
We'll see.
How high do like the
Yeah,
algorithm?
I mean, it has to be uniform as this test.
Quite
You just want to
yeah, the break part is.
I saw, for example, like Lie algebras, of course, like
So that part is still there. I mean, that is, I would not say it goes very deep. I mean, you can go in deep in that direction, but when it comes to
And in some of these
SPDs
exercises,
and relative stuff.
you probably need the mean to be 0 or something. We all just think of it. You forget the same.
Yeah, I follow.
Yeah.
Naturally.
This one is quite simple. So yes.
I mean, this is basically the steps for algebra. And then 1 through 4.
Sorry?
1 through 4 are basically the steps you have to go through to prove algebra.
Oh, yeah.
Effectively, you have to do all these 1 through 4 to prove algebra. Actually, you have to use like a generalization of numbers. You have to do like, if like the conditional expectation of x given some like sigma field, let's say script g is 0, and then you get like this almost sure like inequality that's kind of like similar.
To show that those are conditionally supported.
Yeah, conditional is bad. And then that's how you prove algebra. With number 4 as well, but that conditional. Actually, see, you actually there are like those matrix concentration bounds, right?
Yes.
I'm actually wondering, is there like something
This is one. If you measure concentration, then norm.
Right.
I'm saying that the operator norm is small, we cancel out.
Right. So yeah, a technical concentration bound. Right.
But then here's the operation.
So A minus, I have assumed it will move zero,
Right.
but you can have non-zero mean, then
Right.
it's concentrate about.
About its means, exactly. So this would also give you some lower bound. There's also a lower bound for this one as well, or
Yeah, that's an exercise that
Right,
this
that
is
route,
the.
right, nice.
But
Nice.
second one, and the point is, usually you look at AX. You look at A transpose B or X. Get this is the value. It's motion of X transpose.
That's for square matrix. That's not true for non-square.
Yeah.
Capital O there, the capital O is R.
That's what he told.
That only
No,
R.
Like
is independent.
But the rules with respect to they are good. With respect to saying that with respect to this going to infinity in a certain way, and the constants.
Wait. This is going to infinity.
Yes.
Not necessarily connect.
That's key.
Right,
You
only the-
clarified that even they have to go in a certain way.
I
So he is not specified exactly how this is going to be. There are some conditions, presumably. But the way to interpret this is there is a constant.
Right.
All the R dependence is brought in here. So the constant is dependent. And when you put R equal to 2, this is you'll get root n. But here you have 2. So this 2 comes here. So there is an additional constant here which is weaker with respect to it's not clear whether
right.
he has not said theta equals.
But I didn't see that many put one.
R equal to 2 means that it can be any. No, so it's just now a matrix,
Correct.
but matrix of size which is becoming larger.
Right.
So I think in the matrices case, he says it's just root m. So
So-
bigger was not fine.
Oh,
Yeah, it's not right.
N1 is equal to N2.
N1 equal to N2, so that will give you the 2,
Right.
but with the square root, and then you have a log R.
Right.
So I think that this constant though is 2 root n. So 2 log, what you get here is root of 2 log R. Log 4.
No.
So it's not clear.
Wait, there is a log 2 here. There is a log
Another 2 coming from here. So 2 log 2 with the square root. So I wonder, maybe he has to put R.
What do you mean pull up? Wait.
There is a 2 n1 equal to n2. So you're going to get k equal to 1 to 2. So 2n here.
Oh, where is
So
so square root of
2 log 2. Square root of 2 log 2. But that's, so I think we are
right.
there must be R bigger than or equal to condition.
Like a 10 kilometer. Into the direction. Hopefully, it is not competition. For example, is more. Very important statement. I'm trying to very
So I kind of think so.
yeah, that's right. I'm just saying, they're experts in analytics, so they can pull out and go deeper. Another thing. You also do. Maybe. Everyone can stop. Everything is good.
Where can ask us? Open the call. It's a secret WhatsApp.
Right.
I already told most people what's our group. Oh, they have already actually. They know it. That's the whole form of it. Other than what, possible and all electric of point of view. And then it's actually this.
Sounds like I mean, I don't mind it, but it's like the CD sideways maybe as well, but this is gonna cover it, so.
This side is.
Yeah, and I will just be on this side. We're running quite a bit. The idea is. Complicated. I noticed you do the slides on the screen and then I just write here, but then sometimes you put on these boards and then I'm being on these four in the middle or something.
What is this? Street shares will come from.
Yes.
Slide on critical from.
This from they show the boards.
Slide on the board.
Yeah, at the moment, yeah, I mean, I can change the top to, right, what's on the side. I need them both, yeah.
That's what I'm saying. So if you have this slide.
Yeah.
And these two boards, can you fluctuate up and down this with pushes? It's too small.
It's pretty small. I mean, it's doable. Why, what's wrong with this one? We can use this one, we can use this one, right?
Okay.
I just use it for.
Camera every door is. Pull over. We are taking some.
You can see that board. In the middle, and then, okay. Then maybe, yeah, okay. Yeah, let's go on board. Okay. Really fast. Okay. We'll get through that.
Go.
Yeah, well, that's
இங்க வரும் வரும் அப்புறம் இது வரும் அப்புறம் இந்த இது வரும்
So, and in the last question, how does that relate to the N1 through N3?
All of them are equal.
So is it like N equals N1 equals N equals N key or N equals to B? Yeah, any equation, that makes sense. Because then they're like this and this are like kind of.
You gotta sit down, I'm starting it. Okay, so generally at this session in LPS, we ask everybody to introduce themselves and say a few lines about themselves. But there's too many people. So we got some, and there's also another chaos that will happen soon, which I will reveal now. No food. Lunch is at 2 places.
Wow.
You're going to walk only one of the 2 places. So before that, I'd like each couple of rows along each column to introduce themselves to each other. Rows behind and behind you and ahead of you. Please do it behind you and ahead of you. Please behind you. Behind you. Okay, sit down.
Remember there was this like order at that like critical point in that Parthenon in your PhD. Like you didn't know who was like anti-log and or anti-log and. Have you guys like yeah, right.
Yeah, okay. Okay, the next thing is I have posted on the WhatsApp group the 2 lunch places. I want you to place a thumbs up to the hall you want to go to. Whatever. Talk to people in your group and place 1 thumbs up. You know how to do it. 1 thumbs up, very good. Okay, I know how to do it. Have you signed the group? Thumbs up, which one you want.
Yeah, you're saying. Yes, I done very fast for the previous conversation.
Okay, so broadly we have a split. Okay. Varun, how many in each hall can broadly go?
This one can 45.
This one means
PGA.
PA. Another one?
This one is this.
Okay. So I will go to PGH. You can follow me for lunch to go to PGH. You go into that campus cafe, first floor buffet. It's a nice flashy place. You can follow Keshav.
The PGA is the special dining hall, not the usual dining hall.
Okay.
There is another dining hall.
Okay, some of you have joined late. I know I'll just try to check it.
Happy New Year.
So that's clear, right? That's the only announcement to make. The other announcement is about the clip. I will post it again because a lot of you did not join and then like normally came late and didn't join also. I posted one more announcement about the trip tomorrow. Please, we have to work. There's a Google form next to it. Please sign up. I'm done with my announcement. That's the answer. Okay, so now that lunch is decided, people who joined the group late, there's also a juice message. Keshav will send again. That's for the afternoon. So in LPS, we ask students to ask questions first. And if there are no questions, we just stay silent. And everybody can squirm. People who asked so far cannot ask. When you ask the frame, even during like the actual lecture.
I have 10 minutes only today to 12 tests. Don't be quiet, no students anywhere. Yes.
You asked in the top. You asked in the
Also can ask or ask. Rest will ask.
You can ask last 2 minutes. You will give a test. Just waiting.
You just went?
Every. The students never ask questions. If you're having tablet reimbursement, will ask you one question. No. Then if you ask you for travel reimbursement, you must ask at least one question.
What is life?
What we should connect. Go ahead, Karesh.
Yeah, so I mean, you said you didn't have enough motivation for eigenvalues and eigenvectors of tensors. But now that you have about 5 minutes, I mean, given that you said that tensors are applications, let's say machine learning, and statistics and things like that, what would an application of eigenvalues and eigenvectors in such contexts specifically?
So for I think largest eigenvalue they have application in this Lyapunov exponents which govern the solution of equations. Like linear ODEs, you maximum eigenvalues of matrix gives you tells you how fast solution is. That's one. Here this norm that can be used as a way to measure how a random tensor is concentrated about given sequence. This is a concentration inequality in that sense. So when you apply to, let's say, hypergraph, so the one question would be, can you replace that hypergraph by something deterministic with that? Another thing from here that will come to later is sparsification of tensors. So the result and the other things are you just make it zero. Whereas that sparsified tensor is close to the original in some sense. These are some of the things that I will.
You're a faculty. Wait 10 minutes question. Tomorrow you can ask. The other students never ask questions. Really, you're not student.
Lifelong student.
Lifelong students. I want current students. You ask questions to talk to. I don't talk to us. Don't take photograph of me.
Yeah, I'll come to that later. You can always define empirical distributions and their convergence. The problem is we don't have any analog of how to relate the moments of traces with the empirical distribution. There is no handle on the empirical distribution.
Every day we do this for 10 minutes. Students don't ask questions, we keep quiet. Very clear.
Or completely accurate.
Okay. So who said there is no unique definition of branch? But you also gave expression to obtain singular vectors.
Yeah.
So if for matrices we define.
Yeah, so they don't agree. That's fine. Like, you can define various motions, but they don't agree. So like for matrices, you can have the rank equals the number of non-zero singular. That's one. That could be one definition.
There is no rank nullity theorem.
No, there are certain ranks, certain definitions of ranks will enjoy those properties, but they are not related to, for instance, this one, which they are from matrices, right? So this one would be useful to us because we'll see that the best rank one approximation of a matrix is given by that eigenpair, the largest eigenpair.
Got it.
Just one follow-up. Even though the definition of eigenvalues are different, are there any bounds that these eigenvalues are bounded by the other definition?
Yeah, those type of relations are there. In fact, we'll so one cheap trick on bounding eigenvalues or operator norms, etc., is that you from the tensor you make a matrix, right? You in some way. For matrices, you know how to compute eigenvalues, etc. So you can relate in terms of inequalities this.
You know that the again vectors of the covariance matrix variable often input interesting information. Like for example, they allow you to do things like spectral initialization and things like that.
Yeah.
And it's a very important problem. Just defining again vectors of covariance matrix. If you have this set column there for tensor, like maybe the fourth order.
Right. Obtaining those things utilitarially is very challenging. Like obtaining the spectral decomposition. Most of the time, what I've seen is that people make matrices out of tensor and apply the spectral method there. So maybe you have a problem like clustering in mind where you want spectral clustering. So you do some matricization, do clustering on that. Because obtaining these things are not easy. It is iron driven. Doing optimizations. Oh, so here is one example. Let's say I have a rank order 3 tensors. Right? You think of ij as one mode, right? So then you can represent it as a n1 times n2 vector, the first two modes. You just list the numbers in some order. Like there are n1 n2 many numbers. And the other leg will be so something like x1 1 1, x1 1 2. These are the rules. This is one type of matrixization, which is known as tensor unfolding. Another one we have already seen. We are multiplying by this rank 1 tensors. So if you multiply by r minus 1 order rank 1 tensor, you get a vector. But if I multiply by r minus 2 order tensor, I get a matrix. So this is a matrix called a contraction of the original. This loses information because I'm summing things up, but this, in some sense, has the same amount of information on the entry there.
The multiplication that you defined with tensors, does that constitute some kind of group structure or something?
I haven't thought about it.
Like any algebraic structure at all?
Yeah. No, I haven't thought about it. So. I don't even know whether inverse actually exists.
So that's why I was thinking, yeah.
Yes.
Symmetric tensors can have complex eigenvalues.
Yeah, so we saw an example, right? We took this gamma here, right? And we took roots. We could take complex roots so that. So as an exercise, take this diagonal tensor and take the eigenvector to have all entries equal. Right? And this is just how you get complex roots of unity. Okay.
have short talks in this session. First speaker is Mohan, who's a alumni from here. What do you want? I think show you. I think you have to switch off.
Yeah, thank you very much. Congratulations for having me here, inviting us to speak. Be happy to be here and thank you. So very happy to be here. Thank you, Parimal, for introducing me. Thank you, speak for the other organizers for having me here. So this is a talk that I guess you could say it's an intersection of combinatorics and discrete property. It's about the existence of negative correlation in two very natural models of two natural classes of measures for graphs. First, I'll lay out the story, explain why it is interesting and why it is challenging. And I think that we have been able to make some progress on these problems. Okay. So first of all, let me just remind you of what positive correlation is. So all our probability spaces will be finite, will be discrete, and so there are no measure theoretic or topological certainties. So you have a collection of random variables on some partially ordered space, and then they are said to be two events, A and B are said to be positively correlated if the intersection, the probability of the intersection is bigger than or equal to the probability of the product. Okay, so then we have the notion of a positively associated measure. What this means is, once again, you have a measure on a space, and then for any two increasing functions. So you have that the expectation of f times g is bigger than or equal to the expectation of f times the expectation of g. So if you want to think of examples of positively correlated things, very classical thing is you take population connection properties. A is connected to B and C is connected to B. These are positively correlated things. Okay. And the very nice thing about positive correlation is that you have this thing called the FKG inequality. So let's say that everything is happening, on some lattice. So the FKG inequality says that, so you take the probability measure, you want to check whether it's positively associated or not. There is a purely local condition that you can check. And if that local condition holds, then one has positive association. So this condition is often typically very easy to check. And and then one gets a whole host of correlation points. Okay. Now examples. So the product measures are positively correlated. That is the context of population, ferromagnetic icing model, ferromagnetic quartz models, etc. These are all positively correlated. They're very easy to check by just check the FKG. Okay. And there is this model that is of particular interest to me, this so-called random cluster model. It generalizes both percolation as well as, the icing models. And an introduction of one parameter Q. So Q bigger than or equal to 1 is what is widely studied. So that is a ferromagnetic case. But then in this particular talk, I talk about the mysterious Q less than 1 case, which has lots of connections to wait for it. Okay. So applications of positive, correlation and positive association. So if you have done any population theory, you'll find out that you use this fact that connectivity events are positively correlated day in day out. And then it has a lot of consequences. So pretty much anything you do, in population theory has this positive association that you use in some form, almost on every time. When it comes to spin systems, the icing model and so on and so forth, if you look at how you show that there's a Gibbs measure on for the icing, the photomagnetic icing model on a lattice, that is exactly using the finite kg inequality and positive. And there are also lots of applications, both to combinatorics as well as to the design analysis of algorithms. Now that is the story of positive correlation. What about negative correlation? So in the context of positive correlation, there is this nice and powerful, this FKG theorem, that allows you to figure out if positive correlation holds. And also, it's a nice theory in the sense that it is stable under various operations like tensor products, joins, and things like that. When it comes to negative correlation, the situation is a lot more murky, and there is a beautiful survey that was written by Robin Timmel in 2000. It's called Towards the Theory of Negative Dependence, and in which he lays out that there are lots of fundamental, lots of structural issues that need to be solved. Closure properties don't hold. I don't know any local to global theorem like you have, for FKG. Determining if you have negative correlation holds in some very natural settings can be very challenging, and so on and so forth. Nevertheless, people have proved a number of very interesting results. First of all, examples of that you see negative correlation. Okay, this is something sampling without replacement. You would expect that that you would have negative correlation, and indeed this has been proved in a very broad way. The most famous example, perhaps, are these spanning tree measures. So you take a graph, look at sort of all spanning trees, look at a uniformly random spanning tree, and you look at the event that an HE belongs to a spanning tree and an HF belongs to a spanning tree. It's a very famous fact, which will become evident in a minute. So it's a very famous theorem, classical theorem that goes back 150 years due to Daly, that states that edge events in spanning trees are negative. So the probability that a random spanning tree contains an edge E, given that it contains an edge F, is less than what it was originally. And there are a number of ways of proving it, but maybe the most natural way of proving it is using the connection between spanning trees and electrical. And there are other classes of measures, for which negative correlation has been investigated. So there was an entire theory of these strongly Rayleigh measures, that was introduced and studied around 50 years ago, and this was generalized, to this so-called Lorentzian polynomials. However, now here's the thing: there are, before I get to two very basic questions about which we don't know the existence of negative correlation. You can imagine that negative correlation is very helpful. So particularly, it will be very helpful in proving, enhanced correlation inequalities. There are consequences to proving mixing times for random walks and so on and so forth. I would suffice to say that there are plenty of examples. So it's very nice to have negative correlation at hand. Okay. Now, the thing that, so I'd like to ask you a couple of, maybe a test your intuition thing. So this will maybe, indicate why the situation is different. So here is what we have. So we have a graph, and you take a random forest. Okay. Forest is just an acyclic subgraph. And now my question is, suppose I force the forest to contain a particular HE. Is it more likely that it becomes connected? Meaning, is it more likely that it becomes a spanning tree? Okay. So the thing is, the intuition is, if you're looking at, let's say you forget the acyclicity, and then you take a random graph, and then you force the graph to contain E, is it more likely that it becomes connected? Yes. So the guess is yes, okay. But it turns out that is not the case. So one can construct examples where forcing an edge to belong to a random forest decreases the probability that it becomes a spanning. However, if you look at a related question, if E does not belong to it, you force the forest to not contain E, then you take another HF. Is it more likely to belong to the forest? It is a bit of a mouthful, but it turns out that we don't know the answer to this, and this is one of the big questions of this day. Okay? This is exactly asking what I will write down on the one mentioned in the next page. Yeah, sorry.
Where is it left?
It's also an edge. So you have E and F are two edges in the graph. Yeah, two edges.
One doesn't belong.
Yes.
Other belong.
Yeah, that's the other. I mean,
E and F is uniformly among all of them.
yeah. So no. So uniformly among all forests. Okay. So you fix E and F. You fix E and F. Yeah. Okay. So actually, the thing is, if we are in the landscape of positive correlation, the two problems would be one would imply the other. But in this case, somehow it breaks down. So the two examples, there are two outstanding examples that Robin Fremantle mentioned in his paper, where negative correlation should hold, but we don't know how to. One of them is just the measure on forest on a finite graph. So either you can take the uniform, you can give every forest the same weight, or you can rate it by some lambda to the power of number of edges. So in physics, there's a nice thing called the arboreal gas. So one thing, so these are not rooted forests, so these are unrooted forests. I mean, the rooted forest, the situation is much simpler, about which we know everything. These are unrooted forests. I should mention that counting the number of forests in a graph is also computationally tracked. So it's an example of a /p hard problem. So yeah. Now, the other thing is the so-called random cluster model, which I'll write down the definition of in a bit. And the questions are, it is believed, so Q bigger than 1 is an example where positive correlation. It is believed that when Q is less than 1, negative correlation should hold. But our knowledge of what actually happens is very limited. And these are specifically stated as conjectures by a number of authors, Kahn, Jeffrey Grimmett, Soren Winkler, and Robin Fremantle. So this is the arboreal gas. You take a forest, and then the measure on forest where the measure is proportional to lambda to the power of number of edges. So if you take lambda to be infinity, that means that you're just getting the uniform measure of span. Now, the conjecture is exactly this. So you can think of this as slightly non-standard notation, summing over this. So this is the negative correlation conjecture. This is exactly saying that what we know holds for spanning trees also holds for forests. Now, about this thing, in the lambda is equal to infinity case, we know that negative correlation. This is the famous theorem of T. Then, to give you an example, this is a very natural question. Anybody can understand it in the background, but it turns out that we know almost nothing about it. So we know this for small graphs computationally. We know this for series parallel graphs, which is quite not very difficult to do. Even for the complete graph, we only know that this holds when n is sufficiently large. Even for the complete graph, right? You fix a lambda, then when n is sufficiently large, we know the negative correlation holds. Because this entire beautiful theory of Lorentzian polynomials that were developed here between 2018 and to date, so it was predated by some work of David Gurwitz earlier. You can use all that to show that, they want this to hold. This holds if you put an additional factor of 2. So here, what I'm doing is, this one, every forest has a weight. And then I sum over all forests. This is, I'm summing over all forests which contain the edge E. So I'm writing in combinatorial terms rather than probabilistic terms. Okay. So even for the complete graph, we don't know, that it holds. We only know that it holds the asymptotic result using analytic techniques. And this entire business of Lorentzian polynomials is very, very influential in resolving some of the mixing time problems. However, from a probabilistic perspective, it does not give one thing. And one thing, that we were curious about, together with the focus of mine, at least one should be able to say something when lambda is very large. So the large lambda limit, the lambda is very small is trivial, but when lambda is sufficiently large, it doesn't hold. So here we have, when lambda is infinity, we know that we have this, it is basically controlled by the what happens with spanning trees. However, that spanning tree term, the top degree term, so if you write this thing out, right, so one gets a polynomial, this is the top term that comes from spanning trees. And for a complete graph, for instance, or even for natural graph or the Peterson graph, whatever, this thing vanishes actually. So we don't know what to say. So when lambda is very large, can we say something about what happens to the other terms? And this thing, we believe that this thing can be approached using from electrical network theory. But very surprisingly, not much was known about what happens to the other coefficients. There are some conjectures. Now, in the work that we did, we approached, we tried to approach the other coefficients. So the top coefficient, it turns out, the one that has a very natural interpretation in terms of electrical. So what one does is, you take an edge, you inject a unit current at one vertex, and you remove that same unit current from another vertex, and you get one electrical network on the graph, right? So this will give you a harmonic function, blah, 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 etc. Now, what we do is, first of all, this will induce this electrical network, and then you have a collection of potentials. So the difference of the potentials across that particular edge, this is known as the effective resistance. It's a well-studied quantity. It turns out that the top term vanishes only with the following thing. So let's call this the canonical E current. Ejecting 1 ampere at E minus and removing it at E plus. Let's call it the canonical E network. Then what happens is you look at the potential difference across the vertices of the other edge. Then, and this thing, this is exactly the expression that comes when we study negative coefficients. We use this term called Rayleigh difference. The difference of that, which we would like to show is positive, so that we call the Rayleigh difference. So it turns out the Rayleigh difference can be written, in terms of a quantity that comes from electrical network. Again, it is perfectly possible for this to be zero. And it turns out to be zero in a number of interesting cases, Cayley graph, etc. This thing can definitely be zero. Complete graph is an example, but this thing is zero. Then what we did is, what am I doing for time? Okay. Then we approached the second term, and then we found out that quite surprisingly, so if you look at the second term, we look at this quantity, which is the ratio of the number of forests with two components divided by the number of spanning trees. So this is a quantity that you can associate with any graph. This quantity may not be, in the case of the complete graph, for instance, it is slightly less than 1. It can be bigger than 1, etc. This thing has been studied, from the context of potential theory. What we realized is that if you want to write down what happens, so we are interested in the large lambda case, what happens is we have to look at the second term, and that boils down to showing this particular submodularity inequality. Okay, it's a peculiar submodular inequality that, interestingly, has not been studied in the literature. So we were initially skeptical. So this is something very basic. People have been so many papers that have been written on electrical theory and so on and so forth. Surely this thing should be known. But it turned out that, see, the other thing is, this particular inequality that we are talking about, we show that it does hold. It does not hold in general. So somehow this condition is the fact that, the E and F, that they are uncorrelated in some sense, that is necessary. And what we were particularly astonished to find out is that, Q is just the ratio of the number of forests with two components and the number of spanning trees.
Remove E, it will no longer be connected, right?
Those are minor things. So, but then what it turns out is that, see, there are expressions, for the number of two forests. So there is some pioneering work of, Alan Sokal, etc. But the thing is, when these expressions become, there are a few different expressions floating around. The one that we found, very useful, is this formula using potential theoretic methods that was proved, 3-4 years. So this is an explicit formula for the ratio between the number of two forests and the number of spanning trees. Okay, so it looks complicated. It is complicated, but we were able to make it work. So what we did is, after we did all this, that we found out this absolutely astonishing formula for the second highest. So what is going on here? So let me tell you this. So recall that you have an edge E, and there is canonical E current, and that will induce a potential distribution of the graph. Similarly, that you have a canonical F current. So then this difference, the second highest term, the submodularity expression that we have to show to be positive, turns out to be this absolutely correct. And yeah, so it is manifested bigger or equal to 0 because it's not. Now, the problem is actually I made a mistake in the abstract of it. I said that once we got this, when you said equal to 0, so I thought that it can only be 0 in trivial cases when E is a cut edge or F is a cut edge, etc. Unfortunately, the situation is a bit more complicated and I think a bit more exciting. So when is that? So the top two terms, the spanning tree term and the second term, the submodular term, if it is 0, then the graph must have a very special structure. So that means that the graph must be got by amalgamating two different graphs across a cut set. Okay. So if you look at this set S, so these are, and you look at the canonical electrical network across E, all these points must have the same potential. Similarly, if you look at G2, if you look at the network, from F, the canonical network, then all these points must be equivalent. So they're glued in a particular way. So that is one characterization. Unfortunately, there are graphs like this that exist. Nevertheless, So but the thing is, using this, one can prove a number of things. So one can show that complete graphs, which was unknown, then in a large lambda case, they are indeed negatively correlated. Cayley graphs, and graphs with symmetries, like Cayley graphs, distance graphs, all of these things, it turns out that in the large lambda case, we do have negative. Now, I was going to say a little bit about the random cluster model as well, but I'm running out of time. So I'd like to say, my takeaway from this. So for months, I tried to disprove it. So the thing is, this is a conjecture. I think it is fair to say there are no good reasons to believe that this negative correlation does. Also spanning trees, and then there was a leap of faith saying that it holds for forest system. But one important reason why the conjecture, I should not say should hold, would be good to hold, is the following. So over the last few years, people have studied the notion of a uniformly random forest on lattices. Now, how does it define? So if you 20 years ago, people looked at uniformly random spanning trees on lattices. But if you ask yourself, what does it mean to define a spanning tree on a lattice? So there's a certain restriction in statistical physics. You look at something, measures that satisfy something for the DLR condition, blah blah blah, etc. And what was needed, what was needed in order to prove it was exactly the fact that negative correlation holds for spanning. So that allowed people to define the notion of uniform random spanning tree on lattices and prove many statistical properties. When it comes to forests, if we have negative correlation, we will be able to define a unique gift state. We will be able to talk about sort of a unique notion of forest on the lattice. So it will be good. It will be good, if the negative correlation. But there was no reason to believe that it really does hold. So we tried very hard to disprove it. And the natural thing to do was to look at the second highest coefficient. You can write it as optimization program, etc. We failed, and then finally we decided to prove it, and we got some positive results. And at the end of the slide, if you have the time, if you are interested, I've written down a few, ways in which this work may be taken forward, and we're very happy for any thoughts or comments that you have. Thank you.
With the time, I invite the second speaker to come and set up the Dr. Mohan.
Everyone, welcome to my talk, and thanks a lot to the organizers for having me here. In this talk, I will present some joint work with my PhD students, Shantanu and Shivatula. Everybody is at here, and we will discuss some recent work on the connection between robustness and overall parameterization in the context of contemporary learning. In modern models with a very large number of parameters, there are two things which seem to show up a lot: over-parameterization and robustness. So let me talk a little bit about both of these. So many successes of modern deep learning come from models that are over-parameterized, which means that they have the capacity to learn the input data completely. And this is something contrary to classical intuition, where the idea of also not overfitting. So, an example is for MNIST data, where indeed the number of training points is kind of comparable to or even less than even in things like tutorials. In practice, models don't seem to overfit. However, something somewhat bad can happen. It is so this is a picture from a paper by Zagati, Karamba, and Skibert from 2014. And this is about adversarial example. So here you can see that so we have these two grids of images, and you see these two trucks, for instance, on the top left. And these two trucks differ only very slightly. However, one sees that by doing this very slight change, the classification of this image changes by a lot. So in particular, as this caption says, all the images are in the right column. So the left column is the right column. So every image in the right column are related to the birds. So that's an ostrich. The truck is better on top. And indeed, the point again is the image which causes this output to change completely is completely not perceptible to the human eye. And therefore, these models are not robust, even though they seem to do well, and they seem to not robust. So robustness in general is difficult to define, but the human language way of saying it is that if an imperceptible change, the human eye, causes the model's output to change, then it is not robust. But human eye is, of course, very difficult to define, so I will give some mathematical data which is not the okay, so now what is the relationship between robustness and over-parameterization? It was observed by the authors that indeed simply increasing the capacity causes the network to become more robust. And indeed, one would wonder if maybe the reason why we don't have models which are robust right now is because we are not training large enough models. And more formally, can we give mathematical proof of this observation of the authors? And once the event was made by Vivek and Sergey in 2021, and here this question will come about, what is the meaning of robustness? So let me take some time to explain in detail what this setup was. So think of these two things. So on the left, you have a function class which is smoothly parameterized by p parameters. So this may seem like a mouthful, but the point is to capture things like neural networks where you have a lot of parameters, and the parameterization is smooth, which means that changing the parameters by a little bit does not change the function by a lot. So the map from the parameters to the function has a small interest constant in that space. Okay, so looking at these function classes by which you would like to model your training. And the second thing is that you're now in the classics setup of learning where you have covariates and responses, xi, yi, and they are sampled IID. Okay, IID right. from a nice distribution. So I would say in a slide to word nice things. So this is really nice. So yeah, it's quite realistic. But they show that if you have this sort of setting, then the following thing holds. That if some little f belonging to this class capital F overfits this samples xi, yi, one identity from 1 to n, this word off, then this little f must have a large Lipschitz constant. And indeed, this large Lipschitz constant is what we mean by the model f not being robust. Okay, so indeed, large Lipschitz constant means that if you change the input by a little bit, then the output would change widely, which is what was happening in that example. And now let me talk a little bit about this overfitting statement. So this is now going back to our initial slide. So it said that modern models tend to overfit the data, which means that they tend to memorize all the training samples, and indeed the training samples are not very noisy, which means that you should not be basically all of them because they would have errors. But indeed, we find that modern models do end up fitting all of them. Or at least that's the intuition we are going with here. So, so if we have a model like that, which is overfitting, then the Lipschitz constant would be large. And here comes the relationship with number of parameters, which I will now talk about. Yeah, so here's the thing. The Lipschitz constant is at least, some epsilon times square root of nt over p, where epsilon measures by how much you overfit. N is the number of samples, T is the dimension of the data of xi, and P is the number of parameters. So this is essentially saying that if your parameters P are too small, then your Lipschitz constant is large for sure, which means that you will not be robust. Okay. So in some sense, this is giving some sort of proof for experimental observation of Matthew Mangalore.
Epsilon is here is the, what is epsilon here?
Yeah, so epsilon is just measuring by how much you work. So yeah, okay, so on the right side of this equation, you have this object which is expectation of y minus expectation of y given x squared. So those of you who know this would recognize this as the best possible error that any predictor can get in the square loss. So if x is your covariate and y your response, and there's some uncertainty in this response because of noise, then indeed the expectation of y given x is the best predictor in terms of this square loss. And of course, you may not be able to get the predictor, but if you could, then this is the best thing.
Yeah, this assumption that your train loss is at most like epsilon far away to the best predictor.
Yeah. So in fact, your train loss is doing even better than the predictor. So which is not sure overfitting that you are So of course, if n goes to infinity, then you would never be able to do this because indeed that is the predictor. But maybe if n is not infinite, then maybe your model tries to be too clever and it is like infinite, and then indeed this is possible. So this is the notion of overfitting with which that case and indeed yes. So now there's one to say this. Okay, so okay, so now talk a little bit about how that works. So indeed, in applications, the square loss is not the only loss. For example, for the classification problem, like this problem of Madry McLeod district, where you can classify objects as maybe trucks and birds, then the loss is not a square loss; they call it total loss, possibly. And then one might wonder if such things also hold for the other losses. And in general, what is the largest class of losses for which this can be made to hold? And what's the basic property which causes this phenomenon to happen? So to define that, first let me give you a small
picture overview of fragment divergences. So, given some strictly convex and the continuously differentiable function phi, okay, define these fragment divergences. It's just saying that what is the gap of the function phi from its linear approximation. So this distance sort of thing, dc by x is telling me that how far does the graph of this function rise at y compared to the linear approximation of this function at x. Okay, so this distance in green is the fragment evidence. It may seem like a strange quantity, but it turns out that lots of laws which are used in practice are actually fragment evidence. So, for example, the square laws, the clear divergence, and also the positive. And indeed, it turns out that the result of giving a SNK can be generalized for all such losses. So all losses which are written as a fragment evidence. And now to give a little bit more detail. So what's a nice distribution? So think of it as a mixture of distributions which all concentrate like a normalized W. So as I said in a minute, what's mean? Here there are some constant factors also that is this factor K, which depends on the regularity properties of phi. So here, if you're doing multi-class constant probability loss with K classes, then your K shows up here. Okay. So I guess this is something. And indeed, this holds for any fragment divergence T. I have to give some math background to explain it a little bit more. So indeed, this expectation of I given x is the best expected square loss. And in fact, the key observation is that this is true for not just the square loss, but every fragment divergence loss. And in fact, fragment divergence loss is the most general class of losses for which this happens. And this is a very good result by Banerjee, Guo, and Wang. All this was known before, and I'm not say, but they gave a very nice explanation of this in their paper. And indeed, we show that this observation gives rise to a bias variance decomposition, which can be interesting. So indeed, for square loss, people who do machine learning statistics have been some sort of bias variance decomposition. So we show that one can also get certain decomposition for fragment divergence losses using the work of Banerjee and others. And indeed, that is the key to this generalization. Okay, so I'm not talking much about technical details, but maybe I just flash up slides and a few points. So, firstly, what is this mixture of distributions which normalize and like concentration? So, the thing you need here is that for every LHS function, f of z, where z is your covariant x, should concentrate as if x were not. So, indeed, this is only called Gaussian isotropy, which says that you get this really great concentration. So, technically minus p squared by s squared like concentration, where p appears in the numerator. And indeed, if you have such concentration for every component of the mixture, then it's a nice. And indeed, it's only works for the covariant x. And this is the definition of a smoothie matrix. Okay, don't worry about it. So this, yeah, so the experimental lectures from 5 minutes functions. I just say a few words in the proof, not much. So so we want to say that if you are fitting the training data better than this predictor, then this should cause you to suffer intelligence content. I'll just give you the two-line proof. So the point is that so as I said earlier, in expectation the edges should be large. So only way you're beating the edges is because you only get that. So now this leads to a very So within our attack is as follows. So you try to say that the edge is concentrated around this expectation or maybe something which is bigger than this expectation. And another whole point is that how good a concentration do you get? And another issue is that the GP is a complicated. So yeah, how do you to talk about concentration there? So and this is a place where you use this bias variance decomposition. During this decomposition, you can go from a non-lecture CP, this is kind of complicated thing, to a lecture subject. And then you can use the fact that you have this Gaussian aspirative like condition. And then you use some old school arguments about union term.
Your phi is ellipsis function.
Okay. So P is okay. So P is convex, but the thing is that you assume certain boundedness things, and therefore P is also lectures.
So you use phi is bounded function. It's bounded.
So you assume that you're doing everything over a bounded. So the xi and yi they are compact, and therefore that gives you the a that the constant on P, and that's important. That shows up in all the functions. So K, so again we showed it here to expose the dependency on the number of classes. So if P what the concentric loss, then how many classes are there in that problem? That's K. But yeah, general K is something which I just the constant of P.
So this is also a mixture of isometric distributions.
Yes.
Does the bound depends on the component, like number of components, the mixture?
Yes, but the dependency is not that bad. So like there are components, then there's like a poly R like R square thing.
Poly R.
So if I understand correctly, you are saying that I have a large network and I train it to when it is adversarially robust.
Oh no, we are saying the other way around. That if your network is not large enough and you train it to overfit, then it is not robust. So we're not saying that large network is going to guarantee robust. We're saying that if you don't have that, then
The intuitive reason why K shows up downstairs, like with large K, isn't the problem more difficult? Multi-class? In the Lipschitz constant, why does K show downstairs?
That's a good question. There should be some intuition for it. Again, and look at the calculation again. But that's a good question. So I think the reason is that so if you take classes, then the probability of applying each class is a little bit lesser. So I think that's the reason. But okay, but that's a good question. I don't know. Okay, so I think I just maybe explain the thing I said last slide or do it more. So you have this DP thing, which would be non-lectures a priori, but once you decompose it, you're using this bias variance type decomposition. So we probably have this decomposition for a square loss, which maybe all of the other thing. And at the bottom, we write this decomposition for Bregman average losses using maybe something like C, which is the triangle equality for Bregman average losses. So once you do that, then you get all these terms. And they look quite big and boring. But the important thing is that the only term which really matters here is the last term. Because every other term depends only on a statistic of F. So, or it's something that you can easily given. And only the last term depends on F evaluated at a random point. And here you use the fact that you have this thing called isoperimetry, and now this grad you assume it's some lectures for some n, the whole point is that you manage to get away from these square-like things. So in f of x minus y squared, like on the top box on the left, you get the square over the answer, and then you make that part. And then this last term on the top box on the right, that gets rid of the square on the end. Okay, so that is the only point. You get rid of this complicated DC, the most simple object, which is the grad phi of that. And then assuming that the grad phi is left shift, you can have it. Yeah, so indeed, and then again you can do an argument. Let's just conclude now. So one slide comparison with unit circuit. So they also mentioned in practice that such a result can be obtained for a general lecture class by going via the Ledoux-Talleyrand conversion. However, the resulting terms are very lossy for the constant loss. Because this contraction is going to make you suffer some loss. And indeed, this lossiness can be as big as adequate factor. So yeah, and that's why I was and I think I'll just give an outlook here. So some future direction. So the boring things to do are more realistic distributions. So how to go beyond the CS elementary and indeed like so how to define robustness. So robustness like human eye versus that's a constant. But what I find more interesting is the direction of robust generalization. So here I think we were wedded to this idea of interpolation that we have to fit the train data completely. And a priori there's no easy. How does one go beyond that? And how does one look at robust generalization? Where one has to look at data which you have not seen. So because that's the thing matters and today. So I know if I take one paper on this, it was published in Europe like a couple of years ago, but that was very interesting. So not much on here. So if you're interested in this problem and you have the thoughts, please feel free to talk to me about it. And the URL has the link about paper. Thanks.
Just model the speakers wherever you ask a question. But before that, I think you have to follow Shiva if you're going to Ramani guest house. You have to follow Keshav, please stand up. If you're going to the student cafe. Let's thank both the speakers again. I think if it is not talk about the thing is that if it is not
Check. Hello. Check.
Hello. Check. Hello.
It's like, yeah. It's a good idea. It's a good idea.
You want
Both to be clean. Yeah.
this one?
Yeah. Well, I don't use, we're trying to figure out what the best way to do things. I'm just like, boys. Get on draw. On the board. 56, 40. I'm gonna try is protected here and I'll write on the side. Oh, yeah. No, I'm using board N5. So, thank you. Yeah, that should come.
Can do this. Yeah, how do you do it? That's it, huh? Yeah.
Yeah. Have its slides on the side, and then I'll write on the boards. We'll turn this off, yeah. The slides will be on the sides, and then also. No.
Excuse me, Professor Ross.
Right?
Excuse me, Professor Ross.
That's me, guys. Hello.
Sir, would you be using only the slides or both the slides and board?
It's going to be both the slides and the board. The slides are available on the web page. So if you're watching on Zoom, you can see them that way. But I think you should be able to see all that. You should be able to see both the slides and the board. That's going to be
Pin the things up.
Okay, so so I'm doing a thing where somebody do the slides and then just like take it to links, instructions that are sort of laborious to write down, but are easy to understand or come back next time. And then I'm going to do a lot of work here on the board. So for the people in the room, the slides are on the side here. Maybe not very right in the middle, but okay. The slides are also available on the Dropbox folder website. So if you're really struggling with that, you can download it. Okay. If you're on Zoom, hopefully you can see the board in the slides. Just follow it if you can, and then figure it out. Okay, so that was just it. We're all on the same page. So firstly, I'd like to thank organizers and the invitation. Really great honor to do this event. You have to dance some great people who are giving these tutorials. It's really thank all of you for coming and listening to me talk. Please go to the first lecture. We'll see what happens. Okay, you showed up first. So. Okay, good. So yeah, so my tutorial is going to be an introduction to science methods. Going to be fairly basic. The idea is to really introduce you to the key ideas at the simplest level in the simplest settings, which is still quite powerful. So that you can understand how this works, and then you can go and look at the monographs and the more serious literature, and hopefully you get it. Okay, so this is the story for this whole talk. We'll see how far we get. So the main points I want to make sure we cover are Poisson approximation, normal approximation. Very little. People usually cover normal approximation, but in fact, Poisson approximation is easier and very powerful. And out of the box, without knowing anything about climate, we're going to do that first. And then after that, we'll see how long it takes to get to various things of Poisson normal approximation. And then after that, we can decide if we want various approximation or concentration inequalities. Developed by Stochastic very famously. So topic at the end. Anyway, so we can. And then for the references, so there's huge literature on science method. Most of what I'll talk about is all of my survey. Well, a lot of it is influenced by Poisson approximations are really influenced by this book by Barbara Johnson, which is a very beautiful book. The sort of standard reference for normal approximation is the Shaw book, which is available to me. But it has a very different perspective than anyone else. And then, of course, I'm building on lots of things that existed before that I'm not going to necessarily cite here. There were some monographs stemming from some workshops in Singapore that were quite useful. Short Chatterjee has some very rough notes about key topics course at Berkeley. He has some very rough notes, so those are quite good. These are the key points. Materials for this tutorial, they're available here. This is the same link as on the LPS websites. Good. And then I also want to point out there's a collection of exercises by Greg Turloff. He manages on his homepage. This is his current homepage. So he had a reading group, and he has some notes, but he has a whole bunch of exercises that various people contributed to. So for now, we'll have the slides and stuff on the board. I do have some exercise sheets. I will upload those at some point. Be an announcement. Want me to see this? Okay, sound good? So here we go. Poisson approximation. Okay, so maybe I should just even take a step back. So for science method, it's useful for a number of things, but one thing it's really useful for is distributional approximation and limit theorems. Okay, so the most famous limit theorem is the central limit theorem, and as I said, that's why people normally start with normal approximation and do science method. make sense, but we're gonna do Poisson first. And so what's the Poisson limit theorem? Well, let me write it in a way that's maybe not the most canonical way. So let's say we have x1, x2. This is a sequence of independent random variables, and each of them is Bernoulli with the parameter pi. Okay, and then we just sum up all these. We call it random variable w, the sum of all these xi's. So we just think of it we have a sequence of n trials, and they're independent, and each one has a chance of success. They don't have to be the same, and we look at the number of trials, the number of successes. Okay, so now the classical law of small numbers says that if I look at a Poisson random variable, dead, you say Z here? So I'm American, I'm in Australia, so I'm very confused. So we Z is G in this conversation. Dead. Okay, all right. So then for Z a Poisson random variable, which has the same mean as W, right? And any
Sir, can the camera be panned on the slides for a bit? Because for online people, I think it is just difficult to follow.
sorry, so what do you want me to share?
So I think they have discovered that the screen is shared on the
Zoom.
Zoom screen share on the laptop,
Yeah.
and they can see the camera.
Yeah. Okay. So the Zoom screen it is shared on the laptop, right? Can you see me flinging my hand around here?
Okay.
So then you can see the slides on the Zoom, the shared Zoom screen, and then the camera is up on the board.
Okay. Thank you, sir. It's visible right now.
Okay. Okay. So okay. So then what we say is we want to look at the maximum difference in probabilities that W is in some set A and that Z is in some set A, and that's valued by these pi squares. Okay. So that's this is one way to state this. I mean, okay. So maybe the other way to state it is, I mean, firstly, so let's look at that. Let me just say a couple of things. So the first thing is the mean of W is just the sum, right? So that's just the sum of these, the means of the Bernoullis, and so that's why we're mentioning Poisson, they have the same mean as this guy. The other thing I want to say is that for this bound, maybe a more standard way is that we can bound this by, let's call this like lambda, the mean. We can bound this by lambda times the maximum PIs. Okay. So the way to think about this is if I have a sequence of independent Bernoulli trials and all of the chances of any of them are really small. So sort of none of them are equal to 1 with any good probability, but on average I see some number of them occurring, you're going to be close to a Poisson. Okay. And this is really the Poisson convergence is you have a bunch of Bernoulli trials, sort of the chance of any of them being 1 is 0, but on average you get kind of stable amount, and you really expect to have a Poisson distribution. You expect a Poisson point process. Okay, you need to worry about dependence a little bit, but this is what the Poisson limit is. All right. So does anybody you guys know how to prove this?
Is that n times
Lambda. So lambda is the mean.
bound on what?
This bound here, this pi squared bound. Okay. Yeah. This. So that's just to say, when is this small? Well, this is small if lambda is constant and all the pi's are small. That's the main thing. This is a little bit more interpretable. Okay, good. So you got kind of this. I'm gonna outproof. So we're gonna do a proof that doesn't use sign method, and then we'll do sign method. It'll be Okay, so the proof goes like this. So the standard proof is first as an exercise for any coupling. W hat, Z hat of W and Z. That means these are on the same space, but W hat is the distribution of W and Z hat is the distribution of Z. We have this probability is bounded by this is less than or equal to the probability that W hat is. Okay, so that's an exercise. it's really just, you look at this thing and you break across the event whether you're equal, unequal, and mess around with it, and you get it. I'm not going to prove it, it's very easy. But anyway, if you've never seen it, it's worth doing. You can really just do it. We're coupling, yeah. Okay, so now that's the first thing. Now the second thing is we can write, our random variable, our Poisson random variable Z as a sum of yi's, where the yi's are Poisson mean pi and independent, right? Because if I add up two Poisson random variables, Poisson, and it means just add. Okay, so this is a good way to get a coupling because W is the sum of these xi's. Where these are independent Bernoullis, and now we have yi's, the same number of them, and maybe we can match them the Bernoullis to possible. Okay, that's what we're going to do. Okay, so then this is pi independent. So this is true, and then the last thing we want to do is in order to find a coupling, well, actually, because of the independence, and the independence here is crucial, is if we're able to couple each of the yi's to the xi's, then we can justify independence, extend that coupling to the whole vector of xi's. This depends on the independence. Independence is crucial. So then, this is a claim that we're going to actually prove. So there is a coupling. Xi hat, yi hat of xi and yi such that the probability that xi hat is not equal to yi hat is less than or equal to pi squared. Okay, this is the thing that we're going to prove here. But now we're done, right? Because if we can do this, if we can find these couplings, then we can make a whole vector of the couplings. We just have an independent sequence of them, and then this implies that okay, so then if we set W hat equal to the sum of the xi hats and Z hat equal to the sum of the yi hats, it's okay, it's 19. Like there's no urgency here. We don't want any injuries. Okay, so if we do this, then what we can say is that the probability that W hat is not equal to this Z hat is well, it's less than or equal to this is equal, but anyway, yeah, no, it's less than or equal to the probability that let me write it as this: xi hat is not equal to 1. Right? Because if these are not going to be equal, then at least 1. And then now we can do a union bound, and then this is less than sum of the pi squares. Union bound. So this is this classical proof. All we need to do is show the claim. I like to do this proof because it's got. I mean, these are not things we're going to be using deeply future, but these are really in the realm of stochastic coupling and these sort of bounds that we're doing. And also, this is just a very classical. Okay, so for the claim, well, okay. So now to prove the claim. Well, what do we want to do? We want to come with a coupling of xi and y hats, xi and yi that agree the most, right? Because we want this disagreement to be as small as possible. So good colors. Try orange. So let's just draw these histograms. So we have the histograms here of here's 0, here's 1, 2, 3. Okay, so we'll draw the histogram of this Poisson. So for the histogram of Poisson, we have this height is e to the negative pi. This height is pi e to the negative pi. And then so on. I'm not going to actually draw this. That's okay. They're just something else. And then, so this is the Poisson probabilities. And now what about the Bernoulli probabilities? Well, we know that this is 1 minus pi here. But 1 minus pi is always less than or equal to e to the negative pi. always looks like this. And then, well, PI is always bigger than PIE. This. Okay, so now, the way to think about this is we sort of we want to sample from both of these histograms 2 coordinates at the same time, and we want them to agree the most. And so, how do we make them agree the most? Well, they need to overlap as much as possible. We need to take advantage of this overlap. We can't put removing 1 minus PI probability on 0 for the Bernoulli, so we should put all of that 0 probability onto the Poisson as well. And similarly, we can't put more than this on 1 for the Poisson, so we should put all of that on the Bernoulli. And so for our coupling, probability it's equal to 0 should be equal to 1 minus PI. That's probably they're both equal to 0. And the probability that xi hat equals yi hat equals 1 should be, again, we want to maximize that. So that should be equal to pi e to the negative pi. Okay. And now the thing that you have to convince yourself is that, well, okay, great, this is the best we can do. Yeah. Probability that they're not equal is less than pi. Oh, hat, thank you. Yes, absolutely. So this is obviously what we want to do, but the question is whether we can then match up the remaining probabilities in such a way to make this coupling valid, so that the marginals are correct. Actually, if you look at this picture, we've allocated this for this and this for this. Well, the remaining bars that are sitting above the white have to sum to 1. When I take this plus this, they have to sum to 1. And the remaining bars for the orange also have to sum to 1. Right? So we have the same amount of mass for both marginals. And so, okay, I'm not going to write down all the things, but basically, it's pretty easy that every other probability has to be what's the probability for the Bernoulli has to be allocated to 1. So then it's like, maybe I will write it down. So then the probability that xi hat equals 1 and yi hat equals 0 is just the remaining we need there. That's equal to e to the negative pi, because that's the only other bit that the yi is going to be equal to 0. And then the probability that xi hat equals, e to the negative pi minus 1 minus pi, this remaining bit. So just subtract what we've already allocated. And then the probability xi hat equals 1 and the yi hat equals k for all the other k's is just the Poisson probability. Okay. And then, you can check, like I said, you sort of don't need to check, but you can check the margin. And now, what's the probability they're not equal? Well, that's 1 minus the probability they are equal, which is 1 minus this. Okay. And so that's 1 minus pi plus pi e to the negative pi. And this is less than or equal to pi minus pi e to the negative pi, and this is less than. It's actually pi times 1 minus e to the negative pi, which is e to the negative pi. Okay. So that's the thing. Okay, and then I should just say that this is completely general, actually, that you can always find, when I'm trying to find a coupling between 2 random variables, you can always do this maximal coupling where, okay, so let's just say they're valued, where the probability that they're equal and equal to some value k is just the minimum of the 2 probabilities. We'll come back to that in a second. Okay, good. So this is the classical small law of large numbers. It's sometimes called because it's small. Yes. Cool. Okay, we want to do more than this. What I said more generally is that if I have a sum of Bernoullis and each of them has a low chance of being 1, but on average there's sort of, you see an average number of 1s in the sequence, and there's not too much dependence, then you still really expect to see a Poisson limit. Okay? And that's the kind of setting that we want to think about, we want to work in, and that's the kind of setting that's nice. Okay, so here's just a canonical example. We'll come back to it. We're not going to do it right away, but it's a canonical example of the kinds of things statistics we want to look at and say that they're close. But the first thing is we are all going to go through this British random graph. GN is a distributed distribution of T. This graph has n vertices, and the way we allocate the edges randomly is every pair of edges, every n choose two possible pairs of edges, we just toss the coin. If it comes up head, then we put the edge there. If it comes up tail, we don't. Okay. So I just show a big picture of this, where we have a small number of these. So this isolated edge out here, maybe with an isolated vertex. And the idea is that this happens with probability p, and then back here, that like these edges didn't show up with probability 1 minus. Okay, I'm sure most people were. Yes. Okay. And somehow there's a lot of independence in this model. It's just generated by the Bij, where these are independent Bernoulli P's, right? And this is just the adjacent edges. One there with probability B and 0 there. Okay, but so there's a lot of independence, and you might hope to study this, but actually when we talk about random networks and graphs, like we don't just say, oh, which edges are there and which edges aren't. Right? What we're interested in like macro and micro structures. We want to know things like the diameter. We want to know things like how many small subgraph counts there are, this kind of thing. So these like summary statistics that are quite important. Okay, so the some statistics we care about, structural statistics, number of vertices of degree k. So in case you don't know, say a vertex has degree k if it has 3 edges emanating, or k edges emanating out of it. So this vertex here has degree 3. This one here has degree equal to 2. This one has degree equal to 0. Okay, so that's it. So that's a fairly local statistic that's readable from just looking at the Bernoullis that are attached to it. But if we want to look at the number of them of having degree k, then obviously if I tell you that this vertex is isolated, that tells me information about what the degrees of these vertices can be, because I've eliminated them also. And then okay, that's another one that's a bit more complicated, number of small subgraph counts, such as triangles and 2 stars, which are related to clustering coefficients. So another thing that people talk about, they do this in biology, they call it motifs in biology. It's just you have a very complicated network, and maybe you want to compare 2 networks in some way, you want to look for some statistics, and you say, maybe their local neighborhoods look similar, already kind of complicated. So maybe let's just look at the number of triangles in the graph and the number of 2 stars. Ratio of the number of triangles and the number of 2 stars is some notion of like what I call clustering coefficient. It's like how many of the potential, I'm friends with this person, I'm friends with that person, how many of the potential friends of my friends are friends together. So I don't need to get too much into these, but these are the kinds of statistics we're interested in. Okay, for all these statistics, we can write them as a sum of Bernoullis. Okay, we write them in form W as a sum over some index at alpha, x alpha, where x alpha is an indicator that that structure occurs at position alpha. Okay, and those are going to be a sum of Bernoullis, and we want to know when that's close to plus on. So let me just do these first. So these examples is first in the number of vertices of degree k. I'm going to write W is equal to the sum I equals 1 to n of xi, where this is just an indicator that vertex I has degree k. Okay. And what's vertex I? Well, I just made it more sure. So there's any of these symmetrics. Okay. What about the other one? Number of small subgraphs. That's a bit more complicated. So let's just do triangles. Well, in general. Okay. Maybe I should say. So what if we had, degree equals 2 here? We would sum over all of these vertices and say whether they had degree 2 or not. That went down. That would. These two would. These would. Right? So k equals 2. Example has picture has WB2. The vertices in field they have. Okay. Now, for these small subgraph counts, let's say we have a subgraph H. So this will be like triangle or 2 star.
Okay, I mean, it's gonna be one of them, but they're small examples. And then what we need to do is we have some gamma n of h. The index set here is some enumeration of h in the complete graph. We look at the complete graph and we look at collections of all the possible places that a triangle could appear, and we just list it. Okay. All right. So that's what we have to do technically, but you know, for gamma n of a triangle, we can maybe just be a little bit more ad hoc. This is just going to be I, j, k, where one estimate k, and this means a triangle occurs between vertex I, j, and k. All of I, j there. That's this. So again, we sort of just label the vertices, and then we can just enumerate the triangle this way. Gamma n of 2 stars is a little different because this guy has a distinguished. Yeah, these two are sort of the same. I can switch them, but this one's distinguished. So maybe I write this as sort of I, comma, quite pedantic, but you know, where yeah, all these things are not equal. They're all elements of n. This won't matter so much. Like it's just. And in general, for these kind of arguments, because of the symmetry, it's really about how many their relationships, you know, do them at a time or something. So it's not so important to write down those things. Okay, and then, you know, and then once again, what happens here when we look at W, we just sum over all of those, alpha that are in that gamma of the X alpha, just the indicator that's there. We just look across the thing. And once again, for triangles, I can go, I mean, triangles is a little easier. Here, because it's a small graph, and we can just count the number of 3 vertices in our triangles. Okay, so we have 2 triangles, and see one, 2. Okay, go over all of them. Choose 3. Try to do these things at the board. It's easier when you're sitting down. Okay, and again, you know, these are statistics people care about because it's very hard to describe networks in a global way. So approaches to studying various natural statistics that might describe. Okay, so we're about to do scientific. But first to do that, we want a metric. So what we're going to do is we're going to here I sort of it's trying to be simple here, and I said quite strange metric. Right? Like for any set A, we look at the probability W is an A, and we compare that to the probability Z is an A, and we get a uniform bound over that, right? So it's a very strong metric. It's inappropriate for many situations, but it's a good metric situation where it supports. Anyway, we can name that metric. We can call it the total variation distance, and that's just going to be so the total variation distance between 2 random variables, but it's really the distribution of random variables. Is the supremum over all the events A, where W and A minus just difference of the absolute difference between the probability W is an A and the probability Z is an A over all Z. Okay. So what we showed here before was that for this classical setting with the independent Bernoullis, the total variation distance between W and Z was bounded by the sum of pairs. Okay, and then I'm going to write this in a way that's not very meaningful at the moment, but it's a way that's going to come back as we do settings. So we're going to write this supremum over event A, and we're just going to write these at the expected value of HA of W, where HA is just this indicator that X is. Okay, so then it's just, you know, the point is that this has a certain form where I want to know how close the distribution of W is to Z. And one thing you can think about is I just have test functions. I just throw a function at H, or function H at W, and I throw it at Z, and I take the average. And if those two expectations are close for many, many H, then you expect their distribution to be close. Okay? And finding like classes of H that are wide enough to give you the distributional information you need, but not so wide that
is stupid too big, so to speak. It's like one part of doing distributional approximation. You have to find a metric that compares. Okay, so here we're going to work in total variation distance and these H's. And the reason I'm writing this, this means nothing to many people, but the second expression is right from. Sometimes people call these integral probability metrics, IPMs. Integral probability references metrics. Sometimes they're not quite metric. Anyway, integral probability, because you're comparing, you know, an integral against the two metrics. Right? That's a phrase we're using. But anyway, the point is these integral probability metrics are exactly the right forms. Okay, so this slide is the science method framework in a nutshell. I'm going to try to explain it, but we're going to explain it by doing it. So there are 3 steps for developing science method for a given target distribution. So we want to show W is close to Z. Z is a Poisson distribution. You know everything about it. It's a beautiful distribution. Why else would we be approximating a random variable by it if we didn't know very much about it? And so somehow what we're going to do is we're going to develop some method whereby we use the properties of our Poisson to create a kind of out of the door way of saying something's close to a Poisson. Okay, I mean, one thing to keep in mind, we don't think of it this way because it's a bit more robust than that, but you know, you could just say, look, I'm going to look at the characteristic function of W and see if that's close to the characteristic function of Poisson, right? And when those things are close, we know that the distribution must be close. Quantifying that requires some extra analytic stuff, but that's the idea. Okay, and so somehow what we're going to replace in the sentence, like I said, we're going to replace the characteristic function with something called a characterizing operator. And that's going to depend on the distribution of something of this Z, okay, which in this case is Poisson. And it's called a characterizing operator because it acts on functions from R into R, okay? And when you apply it, you get a function back, and so then I can look at the expected value of that operator applied to f of x. And the point of the characterizing operator is that would be 0 for a very wide class function f, if and only if x has the same distribution. So again, it's sort of analogous to saying if the characteristic function is the Poisson characteristic function, or random variables characteristic function is Poisson, I only have it written only for right? Here we're replacing that with a characterizing operator. So somehow characterizing the distribution. Okay, once we have this first step, we do this other thing, which is really, you know, a sort of ingenious part of science method. None of this is so natural for us to, but anyway, is here. So for some given function h, we're going to solve this linear. In this case, it'll be a linear type equation, and we'll find what we call the Stein solution f sub h. So h is given; it's one of our test functions, and then we're going to solve a f h equals h of x minus the mean under the target distribution. All right. Okay, again, this is maybe not call that h. So the actually notation. And there's some hope of doing this, right? Because the point is, like in order for, like, if I take the expected value under Z on the right-hand side, I get 0, right? And so the only way that I'm going to be able to solve this equation reasonably on the left-hand side is if I have this characterizing property, right? Because otherwise I'd be getting 0 on the right-hand side, but I wouldn't be able to get 0 on the left-hand side for original platform. So it's really like somehow 2 seems like a magical thing, but it's really working in conjunction with 1. Once we have a characterizing operator, you might say, well, I may reasonably be able to solve this equation because the right-hand side has to be 0 always. Okay. So that's just to say that you couldn't stick any other random operator in there. It has to be a characterizing operator for any of this. Okay, so then what we're going to do is the bounding in the form of the right-hand side, right? Just like this previous slide. Expected value of h and w minus the expected value of h z, right? And so what we'll do is we'll plug in where this left is, we'll plug in big W and we take expectation. And on the right-hand side, we get the thing we want to bound, like for our test function h. So for each test function on the right-hand side, we have what we want to bound. And on the left-hand side, we have something else that now we want to bound, okay? And you might say, how is this helping us? What's helping us here is the left-hand side does not have a z, it just has a thumb. So we've traded, somehow in this problem, we were able to find W and Z on the same space in a nice way. But for more complex problems, you can't do that, right? So again, when I come back to here, we're able to do this coupling sort of coordinate by coordinate because of the independence. But the minute there's dependence, I can't just do coupling coordinate by coordinate because I adjust the rest based on the dependence. Okay, so somehow we traded finding W and Z on the same space with only dealing with W, but now having to deal with this these solutions and understanding their properties. Okay, but I mean just bear with me. This all sounds like mumbo jumbo at the moment, but like obviously this works.
This characterizing what is a typically unique for a distribution?
Absolutely not. No, there's many. So there's ones that like the simpler the better because you want to, at the end of the day, you want to get to the point where you're bounding this and W some complex random variable you don't really want to have much control over. And so you want that to be as simple as possible. There's many. You know, basically, I mean, one way to think about it, if I sort of take one of these and then apply it to like a composition here, there's like a chain rule type thing happening. I get another one. There's many ways to generate these, but typically there aren't that many that are useful. Any other questions? That was very just try to keep these three things in mind. Okay, so I'm just going to tell you that sort of what happens here when we do these steps, and then I'll work on coefficient. So the outcome of all of this is going to be total gradation distance between W and Z is bounded by this soup over some functions f. They're not the head functions of this lambda f of W minus W f of W. That's going to be our A f of W, right? That's what it's going to be. So this is really the theorem. So I'm going to tell you how to prove this theorem, or we'll sort of prove this theorem right now. And this soup now isn't over the test function, it's over some other funny functions. These other funny functions are the solutions, are sort of the properties that the solutions generically have for the test functions we're using, right? So on the one hand, we have this h, we solve this f of h, but think of this as like, when we do normal property will be, this could be a differential equation. It's like when you solve a differential equation like this, where you have some A over here, you inherit some regularity properties of the solution from the regularity properties of the right-hand side. And that's what's going on here. Is somehow these things, we know that they're indicators in our case, and when we solve this, we get come down of the function itself and of these first differences. So this is the first difference right there. Okay, so that's going to come from the. So let me just. I'm going to do the technical stuff, but I'm just going to sketch out the three steps really. Okay. So this step one from the previous slide was the characterizing operator. So let me just write it in this sort of, what we now call Stein's lemma. There is a Stein's lemma for the normal distribution that's sort of the characterizing operator as something's a characterizing the normal distribution. Now we call them all Stein's lemma. You earned it. Okay, so what this is okay, so we'll just let W be an integer value random variable. Okay, and we're going to let this A f of k. So this is going to be defined as lambda f of k plus 1 minus k of k, and this is for f just defined on the integers. There's some silly things that happen if you don't restrict the integers, but let's just so f is a function on the integers, and then our operator A takes f to a new function that's just defined this. Okay, that's the definition. We're letting these two things be true. And now the statement is so then the expected value of A f of W equals 0, all bounded f, if and only if W is Poisson. Poisson would be lambda. Okay, lambda's here over here. This is just it's just a way. So this is the characterizing, and this is exactly the property we had on the previous slide, right? This is expected value of AF of W equals 0 for all bounded F, and only if W has the same distribution for plus. So let's prove this, because this is really the key thing. Okay, so this is if and only if, right? Okay, so this way is easy. Easy, I mean, get the value of AW is plus on, and the expected value of AF of W. It's existing, right? It's just e to the negative lambda, lambda to the k over k factorial times lambda at k plus 1 minus kf of t. Right? Now I want to show this is 0. Well, f is very generic as a bounded function. There's no hope of getting a cancellation here, but what do? We just shift this one by 1, and we write this as just a sum over f of k times, this thing shifted down by 1, and then this k. So then this equals sum. Maybe I'm going to get the boundary wrong, but you don't have to worry about it. We want to take this probability, we want to shift it down by 1. We get e to the negative lambda to the k minus 1 over this k minus 1 factorial times the lambda after k. This minus e to the negative lambda to the k. Again, there's a k here. When k is 0, that goes away, so this becomes k greater than or equal to 1. K minus 1 factorial. Okay. All right, those are equal. You can take it from here if I just.
So if we bounded, AF need not be bounded. If F is bounded,
Yeah.
AF may not be bounded.
If F is bounded, AF may not be bounded. That's true. That's true. Yeah, that's true. Because of the K here, right? The W is plus on, that'll be okay.
Oh.
A good question the other way. The other way is all right. We're just getting something out of W that it has a finite mean. Okay, so then, so now, this way, okay, we assume that this is true for all bounded F, which basically means W is a finite mean, right? We're getting something now for the non-bounded case. Okay, now what we're going to do is we're going to define okay, for L an integer, define FL of K to just be the indicator that K equals L. Okay, so this is just, let's see what happens when it equals K. So what happens now, we know that the expected value of A, F, L, and W equals 0. Let me put it over here. Let me do this thing. Now we just have to write in what these things are. This is equal to lambda times the probability that W plus 1 equals L minus, well, W times the indicator that W equals L is just L, and then we take the expectation of the probability. Okay, so you just get this. And so we know this equals 0, and so that just tells you that, just gives you the likelihood ratios. W equals L divided by the probability W equals L minus 1 equals, and this lambda over L. Lambda times the probability W equals lambda over L. Okay, we have to be careful. This is for L not equal to 0. Now let's just say for L greater than 0. So this gives me all the likelihood ratios, right? And so, when this implies that, oops. So this tells me that the probability that W equals L equals lambda to the L over L factorial times the probability that W equals 0. That's what you get on this. Okay, but that's just the plus on probabilities. Now I said it's just integer value. You have to be careful what happens around 0, but once L is equal to 0, sort of this, all the other probabilities where I'm getting W minus 1 will be 0. Okay, good. So that's the, and I guess I should say just very quickly is that like somehow this lambda and that W is like this likelihood ratio is telling you what to put in those spots. And anything that has this, any two functions like this that have the likelihood ratio, you can plug in and you'll get it there. Okay. Yeah.
Guess the size.
Well, so that's what. So okay, I mean these are sort of well understood at this point, but I said there's sort of good ones. For the integer value ones, you basically want something here that's as simple as possible and something here that's as simple as possible, so that this ratio is the same ratio for the integer value, starting at the likelihood ratio. Really works. Any function that you take a ratio and get the likelihood ratio. The general goal is to make it. So that's really where these come from. Okay. So maybe I'm just going to write one thing and then we'll take a break. So for the second thing, we need to solve this equation. We need to solve this equation, right, and find its property. So this part's not hard to do in general. It's just analytic, and so I'm just going to write down what it is. You can solve this. You can solve lambda fa k plus 1 minus k fa k equals the indicator a is in A minus the probability my plus on lambda is in A. That's what we need to solve here. You can just solve it and write down the formula explicitly. And there's nothing very exciting about this. And I should say, in the same way that there's this likelihood ratio story, there's kind of a generic way to write these solutions. That's sort of coming from like some discrete integrating factors, but anyway, it's not that exciting. And there is a solution, f sub h or f sub a, I'll call it, such that it's in this class, right? The norm of f sub a infinity is less than or equal to the minimum of 1 and 1 over the square root of lambda, and the norm of this f a infinity is less than or equal to the minimum of actually 1 minus e. Okay, where this in general this delta operator is the first difference forward difference. So this is just somehow, as I said, you want to think of this as a
F sub A.
for f sub a, yeah. Yeah. So this is the Stein solution. So this was like, maybe I'll go back to the previous one. That was this step here. I call it f sub h before, but it really only depends on the set A. Good quality H. But now the point is that you see there's no A in here. So these terms are uniform over the whole of A. And so when I go to step 3, and I want to bound the left-hand side here, I want to bound the expected value A f h of w over all the h's that are the indicator that have that form. But all such solutions live in this set f sub lambda, right? Give the bounds here. And so I can bound this deliberation distance just by this over this f sub lambda set. Now all the h's are gone, all the a's are gone, and we just need to bound this right-hand side, which only has the w in it. It has x in it, but they have some properties that we can work with. Okay, and yeah, okay. And this works for any integer value w. If you change the metric, it's going to change these properties. The properties come from the solution, from the test functions. If you change the distribution of the target random variable, it's obviously going to change the characterizing operator. But at a high level, these steps are sort of generic. Okay, you have to perform these. Okay, so now what I think you only do this once. If you don't learn any Stein's methods, that's okay. But this part is Stein's method. But now we've reduced the problem to something else, and like that's just a whole separate problem. Okay, so I'll just stop there and then we'll start working on that. 10-minute break. I'm back at 12 after, 11 after. Hard worker. Got to work an extra minute. Oh, this, yeah, this. I mean, the constant, right, but, well, this is sharp, the constant here should be like, they're pretty sharp, they're sharp, so obviously, the thing we need is, the land is large, that's, that's the right man. Because the key thing is that this is the game here, is when lambda is large, you just have to come up with that, you have to put it with some machinery, and then these guys go down the next big and smaller. That's something that I see in the moment. Really. Yeah, that's what some people, yeah. Because these estimations have these probably, right? So, but we're just throwing all out. Because, you know, you want to do like a local or something, then you work on the fine processing. But there's material. No. So that's what I was saying. It's definitely at infinity is a case like this, and at 0 it's like a. So I think it might be like a 0.8. The key thing is, you know, keeping things not only bounded for all lambda, but actually depending on. We'll see that. Yeah. So this will probably machine where you have like a mean areas going on completely. And so there's situations where you can essentially in the couple of the game, but you can work in the deliberation and actually have awesome. Two things are to be valued and they're both normal, they're actually deliberation. Oh, so this is just a like kinds of things. So we'll do an example where we do the data, we'll get down on the telegraph, we can have a triangle. And under some regimes, but some regimes there are normal regimes where the mean and the variance is 1 to 2D, but then I'm going to wait for this shift once. It'd be Erdős-Renyi and then Erdős-Renyi with the parameter P and N behaving well together. Okay, great. Yeah. So there are regimes where you can yeah, you know, no, the other thing I think is we have to. No. I'm saying like that. This somehow when we do this thing equal to 0 here. Like what happens is if I plug in L equals 0, this is the probability W equals -1. So I get lambda times the probability W equals -1 equals 0. And so that means probably W equals -1 is equal to 0. And then I do the same. I say, what's the if I plug in -1, I get 1 times the probability W equals -1 equals the probability W equals -2 times lambda. But then so there's this funny thing that's happening in the boundary where
this is equal to 0, you cannot take value.
It just cannot exactly. That's exactly what you're getting. Yeah. No, yeah. So it's quite interesting with that. Yeah, so we'll do it. Yeah, Gaussian is f prime of x minus x of x. And you can sort of see that. Well, I mean, one way to understand it, like if I take the characteristic function and I plug it into this, and I take the implementation, it gives me a differential equation to the characteristic function. Okay, so that's somehow you can sort of see these that way as well. That's not fine actually. You can have the characteristic function and include the factor of the characteristic function. ODE, and so he worked out his comment, ODE basically, and he realized, oh wait, actually, it doesn't create function. So that was actually the genesis.
You're saying something goes wrong if the function is not integer.
Sometimes yeah, I mean, so it's like this, it's like only, yeah, so somehow, it's like if we started on 1/2, we wouldn't have this magical thing happening, right? So somehow, like, the shift, there might be some way, oh, I shift it plus on, and then I have to just put it adjust. It'll still work, but I have to say that on the boundary something. But its real value, it also doesn't work because like, it's supposed to be like plus on probabilities on 2 sort of lattices. So the ratios would still be right at 1, but it would be like living on, 0, 1, 2, and like 1/2. It's just, for any generic distribution, it should work. Oh, so that's just because these solutions satisfy these things, which I'm not going to prove. It's like very analytic.
Okay, so this is just comes.
It's because so when I solve this equation, so what we wanted to do is we want to solve this for generic subsets A, right? And when I do this, I get these functions FA, and then you can just write down an expression for it. Not a very nice expression, no way, but you know how to manipulate these if you can, and you can show that no matter what A is, they have these properties. And so that means that when I go back to this here, when I'm trying to see what I can either bound the thing on the right hand side or the left hand side. But I know that any each of the this on the left hand side has those properties. So I need to bound this left hand side for all of the observations. But then I said, no, I'm not even care that it's in solution. I just care that those 2 properties, which I know every solution has. So that's why I sort of an equal here. Actually, margin. Yeah, I really only have to look at H's, but I just say, those 2 properties. It's enough to get looking at function.
So now we have abandoned this like the function that we use.
Yeah. So what bigger class than the solution class is exactly. So that's next time. We need to now bound this. Like that's what I said again, but I'll say it again. We've done this. We're done with this. They're bound, and now we need to say, well, great. How is this bound to be bound by? And that's what we're doing. And that's what it's. So you don't actually know anything about everything I just said. You just want to apply this theorem. You just need to. It's like I think the theorem is true, and you don't even know why it's true. I mean, I encourage you to know why it's true. Like I can just apply that. And you can take these out of the box theorems. I work out to do. Yeah, exactly. So if I change the function product, it will change the resolution. Thank you. The property you just have to write down the solutions and like bang away. There's a few kind of ways to do it. Like you just write down a solution and one. Well, actually, I might talk about this in multiple dimensions. We should write down like a version of a T. But anyway, for one dimensional problems, you should write into the solution. Yeah, I was going to ask about the format, etc. Sorry, but he said. Well, I think what he was getting at is these expectations may not exist, but if it's he was just asking because he wanted to make sure all these expectations are well defined. Because I took minus, right? So if one of these things is infinity, I could be infinity minus. So yeah, that should be something as and it's on the website. Yeah, it's just the these, well. I will add more things. Like, set aside. More stuff.
Let's get started. Could be feasible.
And then we do that basically erase all of it. Maybe just the. Let's just erase the one. Let's just keep going. Yeah, I don't think it's like go.
Then this will take the example.
This will go. No, that's all right. We're just gonna keep going. Yeah, go ahead. Okay, all right. Let's get started. Okay, so so if you were like, I don't know, you were in post-lunch, super drowsy, and you were just like, that was too much stuff. It's okay. It's a new talk. Like I said, with that, you know, if you didn't understand anything that happened before, as long as you believe this is true, this thing here, it's inequality. And then if you're interested in bounding the total ratio, this is between some random variable W you care about and some Poisson, then all you need to do is bound this right hand side. And so that's what we're going to talk about, is how to bound the right hand side. So we reduced the problem to bounding the right hand side. The way we reduce the problem works for every W, so you don't have to redo that. Okay, once someone's down the side method for some distribution, you can just use this thing or the analog of this thing. Okay, so two talk.
You saw this checking is easy, but you know,
no, I'm not going to do this. It's very technical.
The answer, if you write, it's easy to check. Or is it not?
It's easy to check. Yeah, it's easy to check.
Can you write down the answer?
I don't have it on the top of my head. I think if you look in the references, I wrote it down in the notes. Yeah, it's very easy to check because it's kind of a it's not that hard. It's some sort of like weighted tail probability of the, you do some like weighted tail probability of the against the Poisson or something, and then things cancel in just the right way when you write it down and get it closer. It's just not very good. If you have to do it once in your life, you can figure it out from what other people have done, but no one in here is going to learn it. I mean, there's very smart people from my know, but I suspect no one in here will learn it.
One question, so you said metric changes the lambda, right? But also changing the target distribution also, right?
Yeah. I mean, you change the target, it sort of changes everything. Yeah. I wanted to say that you know, first you can change the metric and that will affect this.
And also changing the characterizing operator will change it?
That will as well. Yeah.
That will also.
Absolutely. Yeah. Every choice we made, you know, depends on the figure out number. Okay, so so firstly, let's just do the law of small numbers again. So firstly, we want to make sure that this works with the thing we already know how to do. You have a new method and try it on the thing you know how to do, and it doesn't work. Promising, but don't stop. We need to keep trying, but it's not promising. But also the way that this works actually tells us a lot about how we want to bound this. Okay, so now we're back to this law of small numbers. So W equals the sum of xi, where xi are Bernoulli pi and independent. Right? Okay, so now, so the way, and we want to bound. This expected value of lambda f of w plus 1 minus f of w, where this f, I'm not going to write it down, but it's an f lambda. It has these bounds in its problem. So we have on the slide here. Okay, so this is important one way to, very powerful, there's a whole collection of tools in Stein's method to work on this term, WF of W. Okay, we're going to see a number of them. Okay. And somehow this collection of tools is useful for other things. It's the basis of Tardieu's concentration inequalities. So now there's this type of distributional approximation, which is everything I told you about. But then when you bound this, there's this, how do you actually bound this thing when you just work on this WF of W after W? That's what we do here. What's the expected value of WF of W? W is the sum of these things. Its expectation is linear. This, okay. Now we just have to think about this. Xi is 1 or 0. Okay? When it's 0, this is 0. When it's 1, what happens? This becomes the sum of everything else. That's not I plus 1. So we can rewrite this sum Xi f of sum of all the j not equal to I plus 1. Right? F of Xi of W. W is the sum of all. And I'm just saying, when this is 1, I just make that a 1. When it's 0, it's 2. And now by independence, this doesn't. This is by independence, I can just write this thing. Pi and sum j not equal to I of j plus 1. Okay, and then I can write, well, we want to compare that to what? Lambda f of W plus. Lambda is the sum of the PI, so. PI at W. Okay. So now I take the expectation and subtract them. I have the same sum, the same PIs, and I'm just looking at the difference in exacts. Guys, f of this thing. I write it like this. This is W minus Xi plus 1. This is W minus Xi. I minus f of W plus 1. That's the definition. Okay, so we have the Pi times f of W minus Xi plus 1 minus f of W plus 1, and we take the expectation. Okay, so what happens? We have a similar thing if Xi is equal to 0, these are equal, right? Okay, it's 0. And if Xi is equal to 1, then they differ by 1. So we're bounding, a bound has become I times the expected value of f of W minus Xi plus 1 minus f of W plus 1, an expectation. Right? That's what we have. And this is less than or equal to Ti times the norm. Because when Xi is 0, they're equal. This is 0. This is the probability Xi is 1. And then when Xi is 1, whatever this difference is, it's bounded by the norm of delta f. Okay, so then this whole thing is less than or equal to the norm of delta f sine Pi squared. And now this is less than or equal to I'm just gonna write this is the minimum of 1 and lambda inverse times the sum
I would want to n. Yes, all right. So this was, I know I wrote this before. 1 minus n lambda dash one or 1 on there. So I'm going to do both of these things. Okay, so not only have we recovered the law of small, we've actually improved it, right? Because when lambda is large, this is still going to 0, right? Or this is going to 0. Before we just had this thing with the 1 here, and now we have something that's less than. And if lambda is going to infinity, so maybe we don't even have Poisson convergence. We're comparing W to Poisson lambda, and lambda is going to infinity. There's no convergence. This can still go to 0, right? So we can still say it's close to Poisson, even though it's not converging to Poisson. Whereas the other one, we can't really say that. Okay, so not only, so this is very, I mean, this was kind of a big deal when these happened, like this, because there was a big, people like Lacan and other people were working on this law of small numbers, and they had atoms that were like this times, they knew it wasn't right, so they had like 1 over lambda to the 1/4 stuff. So there was some competition in sort of the 80s to get this right, and it's nice that it came along and we just did it. We got it right, you know, in a way that isn't so obvious, or it's not really clear how to do that. Okay. Oh, sorry. This is the improved. This is what we just proved. And so the improvement here is this minimum of 1 lambda inverse. As I said, it's a meaningful improvement. This is a really key thing of this Poisson. It's very powerful in this way. There are many situations where something's close to Poisson with a big mean, and it's not really converging to a Poisson, it's just close to a Poisson. Okay, so that was just to show this works. The next thing we're going to do is a more systematic way that is related to this. It's a more systematic way of doing what we just did, but for situations where we have dependence. Okay. So for that, I want to introduce this thing called the size bias distribution. So let's say we have a random variable W that's non-negative. And here I'll just say it's an integer value random variable. That's not important. But anyway, slide. It's mean, say lambda. And now we say with the random variable WS as for size bias distribution. Sounds like we take the original distribution and we bias against the size. Okay. So our original measure was here, probability W equals K, and we bias it against the size, which is K. But it's the probability distribution, so we divide by lambda, that's the normal. Okay. That's called size biasing. Size biasing comes up in 2 contexts that are like sort of fun to talk about. So the first context is sampling, or that is. Say I want to know how many cell phones, how many mobile phones people have. Some population, I want to be like, oh, I want to, you know, I'm the government, I'm a telecommunications company, I want to know, like, oh, what's the distribution of cell phones, the average number of cell phones per test. So I got to take a sample. I'm going to take a sample, and I'm going to sample people at random somehow. I'm going to ask them how many cell phones they have. Then I'm going to take those numbers, and I'm just going to average them. That's going to tell me the average number of cell phones. So here's how I take the sample. I dial a random cell phone number. It rings, the person picks up, and I say, how many cell phones do you have? They tell me the number, and I write it down, and I dial another random cell phone. Pick it up. How many cell phones do you have? Keep going, and I do this. I get my list of numbers, and this is great. And I average it up, and I say that's my average number of cell phones in this population. Good? And one thing, I'm a telecommunications company, one thing I figured out, nobody answers the cell phone and says they don't have any cell phones. This is great. Everybody's got a cell phone. It's amazing. Okay, so this is an example of unwanted size biasing. So for example, here, size biasing with 0 mass on 0, right? So this is the hallmark of size biasing. So we size bias. If someone has 5 cell phones, I'm 5 times more likely to call them, right? So actually the sample I have, and this is okay, I actually sample the size bias sample. So you can ask me things from size bias, it's okay. So that's an example where size biasing comes up quite naturally. The other one is a continuous version of size biasing, or we can do this with the bus stop paradox. That's, if I arrive at the bus stop, I'm more likely to be in an interval where a lengthier interval than average. Okay? Because I'm sampling the interval according to time, not according to a random sample. I don't want to get too much. Those are 2 concepts. For us, this is maybe not so important, but this is size. Okay, so the theorem is that if I can couple W and WS, W in its size bias distribution, in the same space. That means I couple them somehow. And I have this bound on the total radiation distance between W and the Poisson. Like this, minimum of 1 lambda, not the inverse, 1 lambda, times the expected difference of W plus 1 minus W max. Okay, so this is an out of the box kind of coupling. So let's prove this, and talk a lot about how you did, because we still done a funny thing where we reduced the problem to constructing size bias coupling. So let's talk about how to start. Cool. Okay. All right. So this is what the theorem will be, and then it's okay. So one thing is okay, so just a couple of just a remark here. For a function g. Another way to write size biasing is if I want to evaluate the expectation of the function g against the size bias distribution, this is the expected value g of w over lambda. Okay, that's another way of writing this. This is the way you can define size bias in a more general way. Say it has radically. Okay, but this is good because now you can see. Remember, we're going to work on WF of W. And so now we have a W of W, and we can relate it to the size bias. That's where it's going to come from. Maybe you already see it. That's the first remark. Okay, another thing that's sort of implied by this is that, well, maybe not implied by it, but this is going to be useful. One thing that should be happening, if I plug in W equal to a Poisson, this should be 0. Equivalent, yeah. This is the same. So this is true for, I should say, for n of g. Let's just say bounded. All bounded g. Yeah, it's the same. It's the same. As I said, this somehow it's like if I tell you how to integrate a measure against functions, you know what that measure is, right? So what I'm saying is that this thing is defining a measure, a size bias measure. Because it tells me how to integrate against functions. So this is actually a more general way. And the key thing is if you want to do a probability measure, if I plug in g as 1, do I get 1? I do, because it's becomes 1, I get the mean over. So that's the fancier way to say it is that this thing is absolutely continuous with respect to W, and the derivative of W. It just tells me how to integrate functions. And so vice versa. We'll do size biasing in more generality when we cover normal distributions. Then this one. Okay. Good. One thing, and then as I said, in order for this to be useful, this should be 0. We should have made this thing 0 on the right-hand side when W is Poisson, and so this is just a very easy exercise. It's related to likelihood ratio story is that W. The distribution of the size biased, if I size bias something and I get back something in distribution that's equal to W plus 1, that's the same as being Poisson. So that's characterized by Poisson distribution. I size bias it and then get back to this is a simpler version of think about point processes. If I have a Poisson point process and I look at its Paul measure is condition a point to be somewhere, and you look at how you adjust the best. And the Paul measure of a point process is the same point process back, or technically reduced problem, but great way to hear it. And that's characterized with Poisson distribution. This is like I counted the points, the Paul measure, and I can assign it. If you're into point processes, this is a special case for more general facts now characterizing Poisson. Yeah.
Here, it looks like you're taking F actually equal to the identity F of X and radiation of belong.
No. So I'm going to prove this. This needs proof. Yeah. No, I'm about to prove this. This is I should go here on. This is why I introduced this size bias. So proof of bound. Maybe I'll just put it in the box here. So what's the proof of this box? So again,
we take F in our F lambda, f lambda in our class of solutions, and we bound the expected value of lambda f of w plus 1 minus w f of w. Okay. But what's happening here? I just pushed the expectation through here. Let me rewrite it like this. It's the expected value of that minus that. Right. What's the expected value of w f of w? It's just the expected value of the side bias times lambda. And we have a lambda here. So this is equal to lambda times the expected value of f of w plus 1 minus f of w sine bias. Here. This is, okay, if I want it equal, I mean, two-thirds. This is just literally equal to this thing times lambda, and I have it. Okay.
We got this form.
That we need to bound this to bound the total ratio. That's a characteristic.
Don't have
Yeah. So this is still, we're reducing the problem a little further to coupling the side bias distribution to W. And I will in like one slide explain how we do that in dependent situations. In situations where there is dependence. So at the moment, like we started with was let's bound the total ratio distance between W. That okay, let's bound this other thing with the characterizer. Okay, let's use that to bound this to find a coupling, like we reduce the problem now finding a coupling between W and Canary. Because again, it's not clear. But it will, it really will. I mean, that whole book by Barbara Wilson, really, they don't use language side by side. It's just this theorem. This theorem is the basis. Quite powerful, actually. Okay, so then it's actually equal to this, and then it's less than I can put the absolute value inside, and then this is like f of x minus f of y, and so there's some difference between them, but I can write it as a telescoping sum of all the first differences. So this is just the norm of, this is bounded by the norm of the first differences times the number of first differences times telescoping sum, but the number is just this. Okay. Oops. It's a little annoying to write down. Okay, if w plus 1 is bigger than ws, then you write this as the sum of like ws plus 1 minus ws plus ws plus 2 minus ws plus 1 all the way up to ws plus 1 minus f of w, and then the number of terms for that sum will be this. And if it's the other way, you write it a different way, it's always the same. And then we know that this is less than or equal to the minimum of 1 and lambda inverse, because it's in this and that's what's on the slide. So here it is minimum 1 lambda because I factor out the lambda, and then I have this minimum 1 lambda inverse, but that's bound. Okay, why the coupling here? The coupling is here because to go from here to here, I need them on the same space. I can't write W. But at the moment, what is the coupling of W? No, we're getting there. Yeah, it is. This is just more nonsense. It's more just like abstract stuff. But okay, we're getting there. This is it. We're here. So this is there's a very general size bias construction for sums of Bernoulli's. That's quite simple to describe on this slide, and I'm going to comment it. And it's very powerful. Okay, so let's say W is a sum of Bernoulli's.
We define delta f, which is k plus 1 and k, right?
Yeah.
Like W1, W plus 1.
Yeah, so okay, let's say W plus 1 is bigger than or equal to WS, then I'm gonna write f of W plus 1 minus f of WS as the sum from J equals WS to W of delta f of J, right? Yeah. Now I take the absolute value of that, I have this many terms in it, and they're all bounded. These discrete things, I mean, you know, you can get a long way, although you do get weird boundary effects sometimes. I mean, this is a derivative, this is just, this using like the fundamental theorem of calculus. But no, in the discrete, it has to be careful, because if I write it the other way, I write it a different way, and you need to make it right now.
Entire was built by one or lambda equals minimum of the.
It was the minimum one and then inverse.
That means from the existence of a solution.
Yeah. That's stuff I skipped over. Yeah.
Is it usual that in the correct form or anything?
Well, you know, as I said here, it is, because that was where the gain of this thing came from over the coupling method. And you know, if you do these calculations, it's like these are gonna be more complicated, and we're gonna have like inverse with n and p, and then we're gonna send n and p n to infinity and t to 0 in some way. And the fact that we have this extra lambda, you know, making it smaller will actually extend the range of where we see +1 convergence of triangles.
There could be some other black magic development.
Yeah, that's true. I'm not super. I mean, I think in terms of size method, this is optimal, and I think that this is definitely optimal. That's a Barber and Paul had a paper in '84. This is optimal for the law of scales. That's definitely true. There's no way you can do better with a solution, so it seems like it's pretty tight. Good. Now, now we need to do this construction. So this is the key construction that we need to really like can do a lot of things with this construction. Okay, so how do we? So now I've got a sum of Bernoulli random variables. The index set could be infinite. I don't really care. Like it's just right. This like sum over alpha x alpha. Right. In our case, we'll be finite. We don't need to worry about it. And then x alpha is going to be a Bernoulli parameter p alpha, and we're not going to specify the dependence. They can have any dependence they want. Somehow have to come into the construction, but if lambda is as usual the mean of w, which is just the sum of the p alphas, and in case alpha, in case the index set is infinite, it's finite. But now what we do is let's say we can construct a bunch of random variables x beta alpha. So alpha is in this superscript here. So for each alpha, for each index alpha, we construct a whole other set of x betas that have the distribution of the original x betas but conditioned on x alpha equals 1. Okay, and let's say we can do that on the same space as the original, right? And then what we do is for each alpha we have that, and we're going to sample an alpha. And the way we're going to sample an alpha is not uniformly random. We're going to sample it proportional to its probability of being 1. Okay, so the probability I equals alpha is p alpha divided by lambda. Okay, so these things are 1. So we choose an index at random, and then what we're going to do is to compute the size bias is we force that x alpha equals 1, which we just write as 1. We don't put an x alpha in there, and then we add up the rest of the x beta i's that we have from the ones we've chosen. Okay. And that will have the size bias distribution. Let me just write this in words. In words, what we do is choose an index alpha. Choose an index I with probability I equals alpha equals p alpha over lambda. Okay, and then what we do is we take that index and we just force it to be equal to 1. Okay. Then set x alpha equal to 1. Maybe I should say be concrete here. So given we've generated all of these guys, given we have, this is how we do the test. We usually do it conditionally like this. First, generate these guys somehow. We choose an index I according to these probabilities. Then you modify it. Whichever index you get, you set it equal to 1,
And then you just adjust the rest so that they're correct conditional on that one being 1. Just, this is deliberately handwritten for you. Adjust the rest of x betas. So they have distribution of theta in this kind. So let me maybe we should just do a simple example. Just do. So let's do some of these early training examples. So let's say we wanted to do this for. This is an example we'll come back to. Let's take this construction for granted. But I think probably moment, right? So how would we do this for some statistic that's seemingly untrue? Okay, so let's say W is the number of isolated vertices in an early training graph with parameters n and p. Okay, and this is equal to the sum I equals 1 to n of xi. This, for these xi's, this is the indicator. Vertex I is isolated. G of n, which is any graph. So now let's construct this bias. Does everybody know vertex isolated? Just go over each vertex. We say, have you connected to someone? Yes, we don't count you. You're all alone. Haven't connected with anyone. Connected by yourself. Great. Okay, so how do we do this construction? So the first thing, what's the probability? We choose vertex. We choose vertex I to fix this one. What was it for Okay, let's go. Expected value of W is equal to lambda. What's our lambda equal to? Let's start with lambda. Right. So the probability that this is equal to 1 is 1 minus p to n minus 1. Yeah. There's n of them. Okay. So good. That's first we compute the mean. So this is the probability we're isolated. It doesn't attach to anyone. Okay. So now go up to here. What's the probability I equals alpha? That's 2 alpha divided by lambda. That's the probability that that's equal to 1 divided by lambda. So what is that in this case? 1 on n, right? Because it's just uniform. I mean, it's just uniform because the probabilities are all the same. So in this situation, whenever the probabilities are all the same, you always just get uniform. There's symmetry. Choose a random, treat a vertex uniformly random. Okay. And now what I'm going to do, so let's call it I. That's fine. And now what we want to do is, okay, I want to construct the xi's so that they have the same distribution as the xj, so the same distribution as the original thing, but conditional on that one be. But let's go a step further. Let's construct a GNI that has the whole distribution of the graph conditional on this one being isolated. Okay, now we construct GNI from GN such that GNI has the same distribution as GN given xi equals 1. Okay, so I have GN, I chose my vertex I, let's just call it I.
what do I do now to my original graph to get a graph that is as close to the original graph as possible, but now has but now has same distribution as G and given I is isolated.
It's another industry.
Yeah, we just erase all the edges of the sketch dash back. Yeah, that's the minimum thing we have to do, right? We must, to get xi equal to 1, we need to isolate I, okay? So we go and we say, here's vertex I, let's just erase any edges that are connected to it. And now we're done, right? Because all the other edges are independent. So actually the event that xi is equal to 1, this is just the event, this whole event is just the event that, these, all the edges connected to this were 0. These BEIJs equals 0. The union point J. It's BEIJs for the next. So that's how we do.
Intersection. All of them, given all the.
Oh, intersection. Okay, so then instruct from the answer to that by just erasing all edges connected to vertex I. Now this x beta or xji, beta not equal to I, this xji is just an indicator that vertex j is isolated in this new graph gi. Where we've just erased all. Then we can understand, like, now, a lot of the graph hasn't changed at all. And then actually we're only interested in the change between, this is our WS, it's the thing we've isolated plus everything else that may have been isolated. But if you think about it, many things were not touched at all. They all have the same. So when we subtract, that all cancels. And then even the things that have been touched, in order for them to change their status, they would have to be degree 1 and attached to I. That's the only way they're going to go from not isolated to isolated. They're never going to go from isolated to not isolated because we're only erasing edges. And so we will do this after I do some proofs or whatever. But like we can actually now just from this construction, bound this expected difference between W plus 1 and WS squared. Okay. It's believable at this point. So this is very typical. It's like we have the graph or the whole system. We look at some statistic, then we construct that whole. We take the original graph or whatever, and then we just adjust it a little bit to make it so that it has the right distribution given that x thing. So that's what this sort of hand waving thing means. That's the way to do it. Start with we sample the thing. We want to then choose one of our indices uniform or random in the right way, and then we want to adjust the original structure so that it's so that it has a distribution given that one seed. So this is just how we actually doable.
Is it easy to see that 1 plus sum of this is like minus?
Oh no, I have to prove this, and then prove the thing below it. Yeah. But I realize now, like doing this is sort of getting the overhead's getting. I want to do an example to show you. This is really very doable, actually. We reduced it to a problem where you can imagine, even if W is a sum of things that are dependent, we can do this construction. Right? We can go to one of the indices, force it equal to 1 by just adjusting the original structure, and then see what's changed, and down the expectations. And that's really the power in this. Okay, so we have two things to prove here. Okay, so firstly, that's my claim is that the side-by-side distribution has this. This is the right thing. It has the side-by-side distribution. Then we have to prove the next line, although the next line is actually just plugging into the previous noun, basically. But let's do both of these. So there's two things to prove on this slide yet. But I thought it before. Yeah. Okay, so let's prove this side-by-side construction does the right thing. So we just need to compute, right? Like we want to show that this expected value of G of WS equals the expected value of WG of W over lambda generically for generic function G, bounded function G. That's what we want to show, where WS is as it's on the slide. Yeah. So we just compute. So the expected value of G of WS, well, the whole thing starts first by selecting this random vertex, so we average over that first. You can already see we're getting the lambda bounded. Times the expected value of G of 1 plus sum beta not equal to alpha of X beta alpha. That's the construction, right? We choose I uniformly random, or not uniform. Choose I according to these probabilities. So we average over what the value of I was. It was alpha with this probability. Given it's alpha, this is the value of the size bias constructions. Just plugging that in. Okay. And now we just need to show that that's the same as WG of W. So hard. Because now we can just write, we know the distribution of these things jointly as a distribution of X beta given X alpha is 1. So let's just write this. Beta not equal to alpha, X beta alpha, X beta given X alpha equals 1. That's it. That's all this is, because this has that distribution is just this distribution. Okay. Now, what do we have here? We have this is the conditional on X alpha equals 1, but this is the probability X alpha is 1. This conditional expectation times this probability. So this becomes the one out of lambda here. That the value of G of 1 plus the sum beta not equal to alpha and beta times the indicator that X alpha. Now there's two sort of silly simplifications. Silly. Right? So the first is X alpha is equal to 1, and so this should just be, I can just change that to X alpha, and this whole thing should be, right? Because I'm more together. And the second silly one is I've written indicator X alpha equals 1. Right? X alpha is already an indicator, so if the indicator that's an X alpha, right? So this thing is just, and now there's no alpha in here because that's just W, and X alpha is here, and so I get 1 of lambda times the expected value of the sum of alpha X alpha times G of W. That's just W. Okay, so that's the proof of the construction. But now we just need to prove it now. It's basically the same kind of thing. So down on the slide, box on the slide. So what do we need? Well, we have this minimum of lambda inverse lambda. We just need to start from this thing up. We start from this down, then we just plug in what this WS is. Just plug in what all these things. So we start with, we know that we're starting at the minimum of 1 lambda times the expected value of W plus 1 minus WS. And then we just plug in our construction of our WS. And again, this all we're going to do is average over what output we pick. Times expected value of the sum over all the betas, X beta plus 1 minus 1 plus the sum over beta not equal to alpha, X beta alpha. Okay, but then that's just, I mean, there's an X, this is equal to X alpha plus the sum over beta, not even alpha, X beta. So we just collect these things. We have an X alpha, the ones cancel here. We have a beta not equal to alpha, X beta alpha, but we have for each of those, we match the X betas. We just end up with this here, which is X minus X beta alpha minus X beta. That's just a comparison of each of the X betas. And I should say, like, to give a little bit of algebra here, but you can see what we're doing here is in this construction, what's happening, well, you have the original X alpha, that's not going to be a problem, that'll get P alpha squared coming from this. And then what you're seeing is what has changed in the rest of the graph by conditioning alpha equals 1, or the rest of the system by conditioning alpha equals 1. So it's like this whole bound is just really depends on how much the rest of the structure changed when I condition X alpha. So so this is just the bound before. And okay, as an exercise, you can recover the law of small numbers. I mean, we can just do it without computing. Remember, X beta alpha has a distribution of X beta conditional on X alpha equal to 1. If they're all independent, what do I set X beta alpha equal to? X beta, right? It doesn't change. So all these terms become 0 right here, and all I'm left with is a secondary X alpha, so I get P alpha squared, and I still have a stack group. You'll pick up that exact same down that we did. So that's a good sign that this is sort of the right thing. So even when we have the dependence, we can get it. Okay, another example is so I think I'll just stop there, and we'll just pick up next time. We're really just going to do a lot of examples from here. So this is really, we finally got boiled it down to a thing that it's just a really useful thing. I guess. And so we'll start with some local dependence example, and then we have some other nice bounds that go through a lot of examples. If you want to, you can try this local dependence example. It's not very hard. It's quite tidy down, but it's a good exercise. Try to understand how this happens. So yeah, thank you.
We convene after 4:30. Then there is a discussion.
Discussion.
Yeah. So some of the things that you wanted to elaborate on.
Oh, I'm not in trouble.
Going to trouble the students first, like Shiva. All right. We convene at half. Everything went down to the
Year to year, I just said, oh, the distribution of these things normally is just this is so it's like totally but we are
Anybody wants juice? Some for me.
yeah.
I will add you.
That's right, yeah.
Funny, funny. तुम्हारा संख्या है पर्सनल follow Shiva.
you have convergence distribution, every absolute moment less than 2 plus delta. You know the variance of the mean. So if your moments in isolated case, they need to converge the same.
Yeah, but then it is not possible.
Then it cannot be.
So then how do you?
No, that's what I said. I don't know. I mean, it depends on, like, you want to start with your problem. I would say, look at try to perturb it a little bit. I mean, looking at the moments is good. I mean, you can compute the moment generating function here. The characteristic function or something. Yeah. That's usually the case. So I would look at it, like, think about your problem and perturb it a little bit. You try to get something that looks a little bit like a Markov chain.
No, I mean
Oh, you mean the variance not going to infinity?
not going to mean going to something and standard deviation going to the same rate. Standard deviation going to the same rate with the mean. And that is the problem. Okay, so that's why if you apply the local and the neighborhood, the harness and that is the problem.
Yeah.
So that's why I can't apply the dependence of.
Yeah, I mean, I don't have a systematic way of doing it. There's also, though, I mean, there are situations where the mean and variance is not like the same order.
Mean and the British, I think it should have the same.
So the mean and the variance don't have the same. You still can have normal. So, but sometimes too, when you're doing the local approach, you have to do these like.
And also the thing is
you do these like.
the smart movement is also positive.
The what?
Smart movement is also positive.
Yeah.
So I mean, this is
Yeah, I don't know. I mean, I wish I had I said there's really, once you get away from these credits or.
I mean, I had an example like that. So this kind of scenario.
Yeah. I don't know. I mean, maybe that it doesn't really converge to anything. It's like, you know what I mean? Like, it converges somewhere, but not anywhere that's like that name. You know what I mean? It's just the distribution. So I think for that, yeah, you need to look at like, so is it non-negative? Is that it? Oh, but it's going, but the mean and the, no, it's not. Can you scale? Like, and you can't scale it. Because the mean and the standard deviation is the same.
And the standard deviation.
So you can scale it. Why don't you just scale it by the mean?
Yes, then I just standardize the quantity and non-zero hard limit.
Yeah.
I mean, all the movements are, finite.
So yeah, okay. So you just scale it.
Yeah.
And so you have a non-negative random variable, and then all the moments are growing like n to the some
in the order of mean.
Yeah.
Standard deviation of
Yeah. So then you just scale. I mean, I would just scale it by the mean in the ultimation. Might converge to some non-negative random variable whose mean is 1. What you're saying, like you're saying that you're saying the mean of xn growing by itself. Well, how can n? Then like
standard deviation is good.
Where you're saying if all these things are going like alpha n to the right? Yeah, so then and then this is bigger than your random variable.
Yes,
Yeah. So then I would just look at this. That's okay. I mean, so I would look at this thing. Then I would look for a mark if it's not negative. So that so you have a non-negative random variable, and it's almost like this would converge to something. Right? Whatever. The constant higher order movement is equal to a constant.
Yes.
Yeah. All of that, like all these things you put some use K. That's okay. Yeah, that's fine. So I don't know. It could be a gamma.
For distribution boundary.
Oh, so so if you wanted to be gamma or something, so for gammas, you know, your powers of gamma, like
What's the gamma? I have that equation. I mean, you're using the gamma extension here. I don't.
No, I don't know. I mean, it could just be a weird distribution that doesn't have to have a name or anything like that. So then you want to characterize it. You can say what you can about this. You can maybe find a little differential equation to, you know, for the element transform or something like that. You know, like this is it's not very, like, for example, like branching processes happens a lot. You have a marker. I mean, so the first thing I would do is look for a marker, because that would be see if you can find a marker in your problem. It doesn't have to be an LFN, it just has to be something that grows at the same rate that allows you to get it. So, you know, like, can you compute the expected value of x n plus 1 given fx? Yes, I can. Yeah, and then so maybe you get something, and then you can balance it out and get a mark scale out of it. That would be, yeah, that's what I would do. You can do this. What do you get on this? Do you get anything? How bad is it? But anyway, I would look at that. Look for martingales. Yeah, when you have non-negative stuff that's sort of just growing like this, you want to, martingales are quite powerful. At least to, you know, find the. And I mean, a lot of times, if you can show this kind of stuff, we're probably doing that in a recursive way, right?
No, there's more equation.
How are you showing that this is? How are you showing that it's growing? Well, then maybe that's always quite powerful. Probably martingales is once you know. I mean, that'll show you the limit. Now you know at least you have the limit, and you know what it is. But then you can at least say there's a limit, and then you can start talking about mean, or you can start doing.
I have found the portrait really.
Non-negative martingale. You have all this uniform ability. If you can show that, if you can find a martingale, all the moments it means all the moments. You wouldn't be. It'll be xn plus. It would have to be something divided by. You know, it'll be something divided by some beta. And, yeah, that's growing in the same order, but makes it so that this is sort of x. It doesn't even have to be. It could be some g of x. You know what I mean? Like g of x, and that's what you really want. It's, maybe it's not even linear or whatever. So I would look for some martingale thing. Now, I mean, even exponential martingales, whatever. I think that for non-negative things like that, martingales are quite. At least to get the convergence, they tell you nothing about the limit, which is what you want, but at least you'll have the convergence. So you can start just taking limits of whatever you can get your hands on into characterization.
I have the expression for the general moment. That point is actually converts to
Wow, that's good. No, but then the other thing is the most generative function. Just the sum. I mean, as long as these things are, this is not growing too quickly, this will convergence of the order of zero. That oh, you have some. I really know that it's. Oh, I see. Yeah, but anyway, I would do this.
Okay, that's it. Oh, yeah,
yes. Yeah. Yeah. Maybe the issues are like the.
This what is outside and what is come, what is like donut. Is it Indian donut?
No donut.
You can try anything.
That'll make me tired.
It's like American, but it's already late. Whatever you put in, come on.
Oh, yeah. Long as you've done it to midnight, that's the thing that's. Yeah, okay. Absolutely. With time. Hey, you part of the body. And where actually they only do that. Because energize what that energy is. We saw some of it. What's on it? You need to be wide enough that now I didn't remember. Yeah. So I mean, the idea is, just see if you want to show that this is by using, then you can classify But then there's a minimum class, but usually it's kind of hard. Are usually things that are like bounded with a bounded derivative or whatever. Right? Well, that's what I said. So we wanted to do stuff that like if we and that's the class. And that's it. So bounded with the bounded first derivative. Yeah. You sort of to make that rigorous, you kind of have to do like make it as small as possible. So okay, so for example, I like a lot of times I just like we only had to check for one type of function, right? Which is that function. But I'm at the smallest class. A small class, right? I just need these indicators that was one class we do. It's like just look at the character. That's right. Those are bounded. Yeah, so going this class would be huge. Like once I know what it is, this will be true in any function where the derivatives you have existed. This will give me. But this is if you have diffusion, then this expectation being 0 will be true for huge class. But going this way, you want to the other way. You want to because if I want to say that x has a distribution of z, then I want to have to check for the smallest number of function. So there's a minimal time that once I know this is 0, but then you need minimum one. You want that as well. But like I said, usually it's very minimal. Count it. You can answer that, but feel like, hey, yeah, you can ask the same questions. Okay, so let's begin now. You want to look on it. It's the discussion session. Shiva is not there, so the floor is open to anyone to ask questions. The moment Shiva comes in, then it's restricted to Shiva. Anyone? Everyone else. Okay, students. Time is now restricted. Yeah, go ahead.
One process. Oh yeah. So the question is, we have defined here side bias distribution for. Okay. The side bias distribution for non-negative random variables. The question was, is there an analog of that for point process? Okay. So so the analog, so the point process analog is it's called the Palm measure. Okay, so there's two Palm so basically you have your point process, so you have the Palm measure, it's sort of a measure family. The way it is so I have my point process something like this. This is really horrendous letters for point processes. This is a capital D. But this is our point process, looks like this. And then what we do is for each x, we can sort of define this is equal in distribution to it's sort of the original point process conditioned on a point at x. So this is very This is very hand waving. Okay, so you condition to have a point at x, and then you get a new so this is called the Paul measure, and then there's the reduced Paul measure, which is I don't know, I'll just call it like I'll put a little r here or something. But that's just, you just take the original Paul measure, and I know there's a point at x, and I subtract it off. Look at what's left. Minus. And so then the sort of, okay, I mean, I don't want to get too much into this, but you can write sort of functional definition. You know, so I can, from this definition, I can write something that is compelling that this should be understood as C conditioned on a point at x in a functional way, like similar to, you know, formally defined by you know, by saying how to take expectation of against this function. So you know what I mean? It's like I want to write expected value of g of this pi equals something. It's a little bit more complicated than that because you actually need to integrate over space. Something here. Okay, that's enough. But anyway, you can just think of it this way. But so this is sort of an analogy with writing like the expected value of f of ws equals expected value of w over lambda theta w. So somehow in this point process world, you can define this whole family of these measures, and then when you write this down, you can understand them this way. And then the theorem says that, okay, so a key theorem is that if your reduced, I can just write your reduced Paul measure here is equal in distribution to your original one, that's the same thing as this is a Poisson process. And that holds in like great generality. So now what is this? So then this theorem, only if, so this is the and then if I just count the points, then what this and you know, when I count the points, the number of points in there plus. And so then this is the counting points version of this is exactly that. But I size random variable and I get the original random variable plus one, that's the same thing. So that's the counting points version. And then you can almost see, because this is conditioning to have a pointed x, you can almost see it in this construction. Like this thing, you can think of these x data as like a discrete point process, and we're conditioning to have a point at. Right? And so this is somehow, you can almost think about it at the point process level as this is the well, these x data are the sort of form measure of that. And then what this says is those x data then it'd be Poisson. So that's the story. I'm switching this up because there's a lot of technicalities and I don't remember these things up. If you look in Kallenberg like wrote a readable random measure book recently, not one in the 70s. Recently.
There was an earlier question regarding the non-uniqueness of the operator A. When yeah. For a Poisson, for instance, what would be another couple of examples of useful?
Yeah, so I mean, so the usual way is like, so I know that like, you know, lambda. I know that I already have this one, right? That's really nice. So one thing I could do is, what if I just take a different f? Like, what if I say now I'll take f like w equals wg of w, and I plug it into this. And okay, it's chat, but a lot of times I'll just give you one. And so you can generate just enormous numbers of, okay, so this is one. So f of w was this gives me some operator in terms of g. I mean, I don't know off the top of my head, but it's probably characterizing. but anyway, maybe not just having it 0, but you just have to check these things. That could also do like, f of w equals even just g of w plus 1 minus t of w, and that gives me thing. I mean, somehow it's sort of obviously related to the original, but it's, or this one's actually quite interesting because f of w, g of w minus g of w minus 1, like that, so this gives me a different characterizing operator, but actually this characterizing operator has a good interpretation, a very useful interpretation. Now, if I plug this in, then I get this sort of new characterizing operator, a tilde g of w, which equals lambda times g of w plus 1 minus g of w, plus w times g of w minus 1 minus g of w. So I made that plus, but I swapped the order there. And then you can recognize that this is the generator of a birth-death process where births happen at rate lambda and deaths happen at rate 1 particle, right? And stationary distribution of that is the Poisson distribution. So actually you can, so if you work with this G, you sort of don't get things as nice as, like if I look at it, if I work directly with this and try to look at the properties of this solution, they're sort of not as nice as the F. Of course, the first differences are as nice as the F because they're equal to the F. But if you do this, then sort of not nice things, some less nice things happen. But then you get this interpretation in terms of the generator, and so you can actually write. There's some like, so then this is quite important at the process level. So if I want to do calculus for Poisson point processes, you need to use this kind of Markov generator type thing, and you can write solutions. You can write the solution of this as a solution so that a tilde gh equals h. So you can write there's a Deakin formula for this. So you can write the solution as gh of k equals this integral from here times the expected value of g, sorry, h is h tilde of x t given x naught equals k dt. And what is this xt? That xt is actually the Markov process, this birth-death process. Yeah. So this is the Deakin type formula. It's basically just the way to think about this is like pt h tilde of k. And then if I apply the generator to that, I get a backward equation, right? And that means the derivative in this equal on the derivative.
This seems like a way to solve for the GH.
Exactly. So this is a way for solving for the GH, but you need in this special form. Like we can't solve this one in the same way because we don't have this special interpretation. But so for multivariate distributions and process level distributions, when you want to use time, we're just in one-dimensional Poisson. This is the only way we know how to solve these equations because it's sort of like you just have to think about PDEs. You don't write solutions to PDEs. No, that's not the way. Like, okay, well, we didn't write the solution to the difference equation, but in one dimension you can solve these things implicitly. This little bit I threw under the rug, and I said, trust me, the solution satisfies this. This is a really explicit calculation, but at the multivariate level, you can't write those solutions, and so you have to rely on them. And then you can see, you can get properties that you can see immediately how you get properties of GH from H, right? So what if I look at the first difference of this? The first difference of this is, it's like I look at, it's like I need to look at GH of K plus 1 minus GH of K. And that's like, I need to look at the process XT started from K plus 1, the difference of the process started from K plus 1, and the difference of the process started from K. And then I need to run that from T goes from 0 to infinity, and so I need to look at what they couple, basically. So it has a lot to do with their coupling time and stuff like that. So you can download those first differences using coupling times for these Markov processes. And so it is a really effective way of dealing with these solutions at the process level. So in one dimension, so it has its disadvantages. In one dimension, you can do it directly, so it's better to do. But at the process and multivariate level, you've got to do it. That's the only way we can.
student?
Yeah, technically.
If you have to extend the time for students. Questions? We had a question during the break. For someone who had just got back.
Right, right.
I forgot the answer, but maybe you can question.
What was the question?
I just asked you about the STEAM class. You said it's a wide class of functions, so I just asked.
Oh, right. Okay, I remember. Yeah. So the question was, in this slide, there's this very vague, outline of how this time method works. And the question was, here we want to say the expected value of this AF of x equals 0 for a wide class of functions. F is the same as x has the same distribution Z. So characterizing operator. The question is, what does this mean, wide class? And how wide is a class B? B for this to be true. So basically, I had a couple comments on that. I mean, first answer is there's no real answer right away. It's going to depend on the distribution and the characterizing operator in some way. In a typical sense, okay. And then the second comment is that there's two directions here. So when you want to establish that this is enough, that x is equal in distribution, you want the class to be as small as possible because you want to check as few things as possible. So there's interest in some sense, there's interest in what's the smallest class of function. Now, there's not necessarily going to be a smallest class because there can be one here and then one part of that and a little bit more of something else. It's not perfect order. So it's not clear there's a smallest class, but you want this to be as small as possible. And so my general response to that is that, if your characterizing operator has first differences or derivatives, and you sort of need those to be bounded and maybe some other boundaries. And that's a general kind of comment, but it's just going to depend on the situation you're in, the characterizing operator you have, and that also. And the other thing is that let's say you want to go the other way. Once I know that x has the distribution of my Poisson or my nice target distribution, well, now you know the left-hand side is going to hold for just a huge number of classes. Like your question about, AF doesn't have to be bounded, but I don't care because it's Poisson now. So as long as it's sort of, not going faster than exponential, I'll be fine. So going this way, you sort of want this to be as big a class as possible. And as long as your target random variable has a nice distribution, it would be if it'll just be. And the third thing was actually we did have some answer to this with the Poisson. I mean, we only need to check this for those functions that were like the indicator F, L, J was the indicator that J equals L. And so that was the class we had to check it for. But once we had it for each L once this thing's established for all of these functions, then we know it's Poisson, and that was what the proof was, right? So that's a very small class of functions. I don't know if you're going to get fewer than counted.
We had planted a few questions there. So
okay.
So you want to go first? Okay.
Then a natural way to see why W is nice bias.
One at a time.
Yeah, that's true. You mean in here? Why does this have a side-by-side distribution? Okay, well, this was sort of going back to here that, I mean, one comment I didn't say that I meant to say was that x alpha equal to 1. If I have a Bernoulli random variable and I size bias it, it's just equal to 1 probably. So it was 0 or 1 before, and it can't be 0, so now it must be 1. So this x alpha equals 1 is really playing the role of I size bias this one, okay? And so so another way to explain this is like I choose, I have these independent these random variables, and they all have these means, and I choose one according to its length, the probability according to its average length, and I size bias it. Okay, and then I have to adjust the rest, and then that becomes the whole. That size bias is the whole sum. Okay, and somehow, what I want to say, like, I mean, in the independent case, you can really believe that that's doing size biasing based on just like the bus stop paradox, right? It's like I have each bus comes, there's like 10 intervals, let's say there are 10 independent intervals that I sum up that determine the length of the bus stop. And then I'm going to show up, in order to size bias that, I need to show up at a random time in there. And then that length of that interval is going to be my size bias. Well, you know, if I'm going to size bias it, the first thing I would do is choose which of the subintervals I get into. It's the length of the subinterval, the chance that I choose a subinterval of some length should be proportional to its mean. That's where this probability I equals alpha, this is the mean of x alpha, so it's a proportion. I'm already choosing that subinterval proportional to its mean, according to length, according to size. And then once I know in that interval, I need to size bias that one, but I don't really. Because then once that subinterval has happened, then everything's back on track, basically. So that's kind of the way to think about it. I mean, I don't know if that really helps because you already have to go back to the bus stop paradox. But that's a little bit how I think about it. Some independent cases in the bus stop paradox. But I don't have any, you know, between that intuition and just doing the calculation, I don't have.
Alpha was behavior of isolated. Alpha was chosen to be behaviors of the remaining vector.
Right, whether they were isolated after
Yeah.
we erased all the edges.
Yeah.
Yeah.
So here, in that case, the law, this equation is
Right.
I'm saying the other variables are independent. So the other nodes being isolated is independent from once you remove it.
Well, it's
that case.
it's not no. It's like, okay, so I mean, well, okay, I don't know. I'm not sure. The way I'm understanding your question is you're saying, so let's say we chose vertex I. So we choose vertex I and isolate it. And then so that gives us like V and I, right? And then okay, so let me just draw a picture. So here was vertex I, and here was the let's just do GN. Okay, so this was vertex I, and then these things are attached to other things. Let's just graphs, whatever. Okay, and now this was some, you know, EIJ. This is some EIK, and these guys are all independent. This is some ELM, whatever. Okay, and what I was saying is okay. Now, if we want to, G and I should be contribution to GN given xi equals 1. Now, this event xi equals 1 is these edges cannot be. I must erase them, right? So to get to GNI, I have to erase them. I mean, that's just there. So I must first do this, and I've erased all these edges. They're all gone. And then now I might need to do another step. That's really so that's what I've done. Now I might need to do another step, but you see, this event is actually equal to BIL equal 0 for all L not equal to I. So I've erased all those. But now all of the other edges that are out here, edges and non-edges, those don't have any I's in them, right? This is the collection B, K, M, or K and M are not equal to I's. Oh, strength. And these guys are all these edge indicators are independent. So the point is, once I've erased this, which I must do because that's exactly this conditioning, I need to adjust the rest of the graph so that it has the right distribution conditional on that. But these were sampled independently of the stuff that I've erased, right? And because of that, but now the question of whether this guy is isolated or not is not going to be independent from that at all. So none of these are independent It's just these edges that are independent. So we still need to figure out how to bound this. And so we will do that. But I mean, I can just tell you that like, you know, X, you know, I mean, it's what's going to happen here. It's actually even simpler, but you know, what can happen here is I originally started that this could have been isolated. If it's isolated already, I erased edges. It's still isolated, right? If this thing's not isolated and it has degree bigger than 1, and I then removed at least one, at most one edge from it, and so I can't have isolation. So the only ones that have changed were the ones that were attached to my alpha here and had degree 1. So in fact, let's ignore these. In this sum, we can write this in kind of simpler way: x beta alpha minus x beta. This is just equal to the number of degree 1 vertices attached to alpha. Right? That's it. Those are the only things that's changed. They have the degree 1. And that's like, you know, we can, and then we can write that as another like thing, again, not equal to alpha of, you know, alpha y sub beta, where this is just an indicator that beta has attached to alpha, and it hasn't attached to anything else, right? Beta, I don't care what happens over here, anyway, that's what it looks like. So I can actually bound the mean of this. The expected value of this is just n minus 1. There's n minus 1 other potential edges. And what's the probability that that beta attached to alpha and attached to nothing else? It's just p times 1 minus p to the n minus 2, because I have to attach to alpha and I have to attach to nothing. So, I mean, so I just bounded this for us, right? This, we just use triangle inequality, we get a p alpha squared, which we know is p alpha squared, we're never going to get away from. And then we have a plus this term. And then we computed the mean before and the p alphas. This is it, so we've already done. But the key thing is not, these are not independent, but the independence is coming by peeling back to the original structure. And that's why I did that example, because it's like, it seems how am I to construct these x betas giving x alphas equal to 1, but you don't really construct them directly. You go back to the original structure that you're looking at random variables, and you construct that whole structure conditional on that event, and then see what's changed. That's really the way it works.
Open for anyone first.
They're the big kids.
Independence.
Well, there's no constraints on dependence. I just want to emphasize this is not the independent case.
Sometimes we have a common compiling alpha, and on that you have indicators which are coming from the SRSW board, and the interpreter like that. Those indicators are involved in the X alpha. Then this method works.
Yeah, but that's because again, we just kept reducing the problem to other things. You still need to construct these x beta alphas so that they have the distribution of the original x betas given x alpha. You need to do that on the same space. And so that's why any dependence works, because the dependence is being captured through these terms, right? It's this x beta alpha. This is joint. You need to do the construction for every beta not equal to alpha at the same time. So the joint distribution is just in on the right hand side.
In your proof, when you are inserting the indicator x equals to 1, then how that things happen in this case? I mean, when you are proving this.
Yeah. So we had again, it was really just using that equality and distribution. It was all about the equality and distribution. So what we had was this sum p alpha over lambda under the expected value of t of some beta not equal to alpha. That's what we had, right? That's what we had, and then what all I'm using is that jointly these x betas have the same x beta alphas have the same distribution of this variance. So this under this expectation, it's just the same as the expected value of G of the sum beta not equal to alpha of x beta plus 1 given x alpha equals 1. These two things are just equal because distributionally that's equal to this conditional distribution. So that's what I'm saying. So that's the magic, is going from here to here. The trick is that I just assumed that, somehow the joint distribution of the x betas are in here, and I assumed we're able to do that construction. And then once we have that, we're just going on with it. So then in the next step, you see this is like a conditional, there's just a generic, the probability of A times the expected value of some, function given A is just equal to the expected value of Y times the indicator of A. For any of A, that's just the definition of conditional probability. Like this is just this expectation divided by the probability of A. This is real. This looks fancy, but this is just. This is a positive probability of A. This is really. Yeah. So now we have this is A. This is the event A. This is the random variable Y in this case, and so then this just becomes the lambda comes out, and we just have to sum over alpha of the expected value of G of beta not equal to alpha x beta plus 1 times the indicator of x alpha equals 1. And then, like I said, if x alpha equals 1 on this indicator, this is just equal to W, because it's like I'm adding everything that's not alpha, x alpha, but x alpha is 1, so that 1 can become x alpha, this becomes W, and then this indicator that x alpha is 1 is just x alpha, because x alpha is alpha.
What I say is that in the x alpha, there is a indicator beta coming from SRSW word. That means all the indicators are, very much dependent. So,
yeah, they are dependent.
Yeah. Do that equality law of experience.
Yeah. That's it, because it's because this is okay. Maybe I should have put it parts correct. This is saying the joint law of x beta alpha. All the betas not equal to alpha is equal to the joint law of x betas given x. That's the critical thing. You can't do it one by one. You need the joint law of all of them. So to go from here to here, this is a function of all the x beta alphas. And so it needs to, I can only replace it with all these x betas in conditional if I have that joint. So this is the critical, that's what I said. The dependence is being inside of here, and that's where we're hiding these steps. But
can you go to the sorry?
But yeah, all I'm saying is that we just kept doing this, right? And this whole time I would do something, you'd be like, yeah, what now? What do we do with that? Wait, how does this work? And so we're just kicking the can down the road. But as I said, with this, we finally got a bound that's just in terms of these things. But now the rub is how to do this construction. So in any problem, this is particular. Sometimes more difficult now.
You can go to the size biased and then this one. So it looks like the F that was constructed, the solution that we had to identify, and then you had a bound. All of that played a role only in coming up with the constant min 1 lambda through the delta F.
Well, in fact, it's bounded. It all is something. You know what I mean? Like to show that the solutions, are bounded themselves, or that their first differences are bounded, in a way that.
And it seems like a somewhat roundabout effort to come to this coupled construction and the bound based on that. But is there a direct way to come to this?
Oh no, I don't think so. That even goes back to see this question earlier about the optimality of these things and this schema. As I was saying, like in the independent case, the Stein method gave this down min 1 lambda inverse is pi squared. So I don't know of another way to even in the independent case with this. So as I said, even in the 80s when people were sort of working out this theory, people were trying other things. Good camp paper where he had landed in the -1/4 here. That was like the best, and then I don't know if it was Andrew or Lewis can. One of them sort of work this down. Right. And then this is, as I said, there's a little down due to Andrew Barber and Peter Hall that this is correct and more general, but certainly the community is correct. So I don't know another way to get it. So I don't know another way to get this because this is, or sorry, the size bias one because that's sort of more general. You know what I mean? And it still has that correct factor.
Okay, I think back to Shiva. Thanks.
Oh. If people are presenting posters, can you come home? Today. Okay, so who else is there? Anybody else is there? That's it. Okay, so they are presenting posters today. They have 2 minutes to sell their poster to you. You can go see them. Okay, get clear? I guess clear. Right? We also is clear. Right? So I will press an alarm at the 2 minute mark. They stop. Okay, wherever you want. Okay. Jack, you go first. Go. Anyway, yeah. 10 seconds over.
Speak on the mic.
5 seconds over. Yeah. Yeah, Bishak, what's going on?
Hello. Yes. I'm Vishak. I is the student for my cycle. So what I'm talking about today is joint work with my supervisors. We have looked at linear matrices with dependent entries in this project, and the dependence comes from the fact that we start with a double index Gaussian stationary process. And can you use the board? Can you use
2 minutes, whatever you want to do.
So the matrix of interest is defined by setting its entries from the stationary process in this way. So by default, it's symmetric. And we are interested in the largest second value of this. The bulk of the spectrum of this model is studied by and one further several years back. I'm looking at the edge of the spectrum. And we express the largest eigenvalue using a very elementary tool from our linear algebra as a supremum of over this unit sphere. And also we can take it as a supremum of Gaussian process indexed by the unit sphere. And then the very well-known tool is probability inequality. Okay. Implement the necessary unknowns and repeat it into the probability inequality. The main result is that is again the scaled by its expectation. Number is going to a weaker, so that all is 1. That's all. Thank you.
Next.
Hello all, I'm Tejashree, I'm from INC. My poster is about multi-reader multi-case study. It is a framework that is prevalent in medical imaging field where whenever there's a new modality that comes up, how do you compare it with the current standard? Usually there's Gaussian modeling followed by hypothesis testing done. But with AI coming into medical imaging, we cannot use the same framework because now AI is both a reader as well as a modality. So we have come up with a new statistical validation framework and a new modeling technique. Please check out the poster for more details. Thank you.
Hello, I'm Ganesh from IIT Madras. I'm a PhD student under Professor Sri Krishna Bhashyan. And our work is data sequence clustering under bandit setup, which means The traditional data point clustering has been well studied in the literature, in which we will be grouping the data points into clusters. So in our work, in the place of these data points, we will be having a data sequence. So we will be grouping this collection of data sequences into clusters. And we assume that each data sequence is a sequence of IIT samples from some parametric distribution. But the parameters are unknown to us, but we can observe the samples from this data sequence. And we consider a bandit setup, which means at each round we can adaptively choose any one of the data sequence and observe a sample only from the data sequence. So the objective is we need to identify the true clustering of the data sequence by using less number of samples as possible and for the fixed error problem. So for this problem, we have derived a lower bound on the sample complexity, and we have also derived a optimal algorithm to solve this. Optimal in the sense the upper bound of the sample complexity matches the lower bound. Yeah, in the poster we will be discussing more details of the algorithm, but also the applications and some of the related works in the current images. Yeah, thank you. Easy.
Good evening, everyone. I'm Dinesh from Isagopal. My poster title is Robustness of Stochastic Optimal Control for Switching Division with In-Cut Model. So, what we have done is we know what is stochastic optimal control. It deals with the decision making under uncertainty. So, given an objective, we try to design control strategies for a system that evolves randomly over time. So, but in reality, we know that the systems are only approximation of the two models. So, we have approximating model and the two models. So, based on this approximation model, we design our control strategies, and and we design control policies from this system and implement on the two systems. So the natural question from here is whether this optimal control of the approximating model is near optimal on the two model or not. So we have shown that under suitable assumptions, this if this approximating model converges to the true model, then the optimal control design for the approximating model is asymptotically optimal on the true model. So we have studied four cost criteria for finite collision, infinite collision, and for if we want to control our system for a random time, then these optimal controls are asymptotically optimal on the. So you see in my question.
Hi, myself Himashish. I'm a fourth year PhD student at IIT Kolkata. My advisor is Somentundan Mukherjee, and I primarily work on random matrices. So today we'll be interested in a random tensor model. Roughly in our model, we consider a symmetric tensor with roughly IID Gaussian entries. We shall call this Gaussian orthogonal tensor ensemble or GOTE. If the order of the tensor is 2, then it boils down to GOE or Gaussian orthogonal ensemble. So we'll be considering contractions of this GOT, which will be matrices, random matrices, and we'll look at the spectral properties of this matrix. Thank you. Please complete.
Hello everyone, I'm Stochastic and I'm from IIT Palakkad. I'm working in the area of information geometry under Dr. M. Ashok Kumar. So my title of my poster is a generalized grammar form in the context of robust estimation. So in information geometry, we consider the statistical models are differentiable manifold where each point on the manifold represents a unique probability distribution. And using English theory, from a divergence function, we can define a Riemannian metric on a statistical manifold. And based on using from the Kullback-Leibler divergence, we get Pisarwa metric. And based on this metric, Amari and Nagoga give the information geometric proof for our user camera bound. One important thing about the camera bound is that if some estimator attains the lower bound, then the variance of that estimator is the asymptotic variance of the maximum likelihood estimator. So in my poster, we first apply the egosis theory to the persuaded divergence, which is popular in robust estimation, and obtain a generalized Pisara metric. And based on this metric, we establish a generalized Camara bound using Amari-Nagoga framework. And one important thing about our bound is that if some estimator attains the lower bound, then the variance of that estimator with respect to the true model is equal to the asymptotic variance of persuaded estimator. So similar to that usual Camara bound, our generalized bound sets the benchmark for the variance of the estimator in the persuaded estimator framework. And this bound has potential application in robust systems.
I have to apologize one thing. Introduce yourself. Your name and affiliation. Name and title. Only name and affiliation.
Okay, I'm Vishal Bhattacharya. I'm a PhD student from ICIT.
I'm Tejasvi from IISc Bangalore.
I'm Dinesh Chandran from IIT Madras.
I'm Jinesh Rathia from Aizaru.
Himashi Salukdar from ISI Kolkata.
And I'm Satyajit Dalmia from IIT Palakkad.
I'll follow them or Subhajit.
By difficult to construct that's
Well, I just mean that like once you can count that, you can compute the bound. But like the difficult part of using the bound, like this bound in the bottom.
And then,
What I'm saying is, all of this is very easy.